Nilesh, good morning.
Good morning, everyone. Good morning, Nilesh sir and Padmanabhan sir, and all dear participants. Welcome to 6th day of this joint faculty development program on designing with FPGAs. Today, the first session will be taken by Nilesh Seval sir on FPGA acceleration. Before that, we would like to share his brief profile with you all. Mr. Nilesh Seval is technical leader at Intel's Programmable Solutions Group. He has 22 plus years of industry experience. Over the years, he has contributed to the system architecture, designing with FPGAs, microprocessors, and custom ASICs. He has a strong background in networking and mobile platform ASICs and has been active in development and validation of ASICs in these domains. Nilesh sir has front-end development ASIC team in interaction with post-silicon validation teams and firmware software teams. Nilesh sir has played key role in resolving customer issues in association with TAC teams. Nilesh sir holds bachelor's degree in engineering from University of Pune. Nilesh sir, good morning and welcome to the session.
Thank you, Biplav. Nilesh, you can share your screen and then we can see whether you are able to view it. Biplav, you can give sharing permission to Nilesh.
Yes, sir, I have shared with him. Nilesh sir, you can share your screen.
Some of them are telling that they didn't receive the link for today's session. Can you please look into it, Biplav?
Yeah, definitely, sir.
Okay, right.
Yeah, please let me know if you are able to see it.
Yes, but it is not that in presenter mode, Nilesh. It's not in full screen mode.
Okay, give me a minute.
Yeah.
Yeah, please let me know if you are able to see the full screen mode now.
Yes, Nilesh, it's fine now. Absolutely.
Okay, thank you so much. So I'll start now.
Biplav, can we wait for some time? There are around 50 plus participants, or shall we start?
Sir, we can wait for a few more minutes. Thereafter, Nilesh sir can start.
Yes, Nilesh, we can wait for 3 more minutes. By 10:10 we can start.
Okay, sir. Please let me know when I can start.
So we can start now, Nilesh.
Okay. Hi everyone. Thank you for joining today's session. My name is Nilesh Sable and I'm part of Intel FPGA development team. So today I will take you through the acceleration using Intel FPGA and also through the details of how the implementation is done. So this is the agenda for today's presentation. So we'll start with the introduction to data center and how the workload acceleration happens in the data center, as well as on the standalone machines, right? How the Intel FPGAs can be used for accelerating the workloads. And then we'll get into the details of hardware and software. So when it comes to the acceleration using FPGAs, we have readily available hardware called as programmable acceleration cards. So these are the pre-developed cards which are in the pluggable form factor, and these use the Intel FPGAs as the main hardware, and then associated hardware to connect with the host. And one of the main important protocol that is required to create this hardware is the core cache interface. In the short, it stands for CCIP, which is used to connect user-developed acceleration hardware with the rest of the system in the using the pack. And on the top of this hardware, we also have a software layer. And this software layer, when it comes to FPGA accelerated cards, it's called as the Open Programmable Acceleration Engine, OPA for short. And this enables connection of hardware with the user interface. It provides a set of APIs which a user can use to fast track his development. So OPA is a set of rich library which contains software components as well as the firmware components, and then user interface components which will help in acceleration of the overall development. And once we go through the details of hardware and software, we'll walk through the entire development flow using the FPGAs and cover all the details which user will be able to find useful in developing his own applications using this program. And then at the end of it, we'll go through the Q&A. Any questions, if we have, please keep putting them in the chat window, and then we'll respond to that at the end of the session. So before we get into acceleration, it is very, very important that we understand about the data center, because when it comes to acceleration, one of the main use cases is in the data center. Of course, the standalone workloads are also helped by acceleration, but when it comes to data center, it adds a lot of value. So I believe that everyone here has some understanding of data center. So, but I'll go through some details here. So before we had these massively scalable data centers, any organizations that has the digital workload, it requires a certain form of data center. So this data center can be as small as a few set of servers within a room, or it can be as big as multiple floors of a building, and multiple buildings together. With these buildings filled with racks and racks of servers, and then entire infrastructure around that to maintain the data center in terms of operations, and as well as the infrastructure required for in terms of power, security, and other stuff. So we know nowadays that everyone is moving to cloud, and cloud is nothing but abstract for these big data centers connected via network to the rest of the internet. So before arrival of these cloud data centers, every organization used to have its own data centers, and these were maintained by the IT staff of that each individual organization. But maintaining own data centers has its own problem, wherein you need to have your own hardware, you need to have a software required to run that data center, and you also need a set of skilled people who can maintain the data center. Overall, it adds with a lot of cost of the running cost of the organization. So nowadays there is a trend wherein the data centers are getting centralized. Now with this cloud data center, there is no need for each organization to maintain its own private data center. So massively scalable data centers are available from players like Amazon AWS, Microsoft Azure, Google Cloud, and then we have Alibaba and Tencent. And nowadays there are many players in India as well which are developing data centers required for different applications. So we have different set of data centers. As I said earlier, there is a private data center which is maintained by the each organization separately, and which is moving toward cloud data center now. And then there is also a hybrid model wherein organization can choose to have a mix of its private data center as well as the cloud data center. So when it comes to cloud data center, even though they provide the cost efficiency and operational efficiency, there are also concerns about security. So there are many sectors, for example, defense, government, finance, which have very sensitive data, and they may not want to have that sensitive data in the public data centers or cloud data centers. So these organizations maintain a hybrid data structure, hybrid data centers, wherein sensitive applications will run into their own private data center, while the other applications which are not so sensitive can be run into the cloud. And then this entire orchestration between the cloud data center and private data center is done by that organization. So there are now many applications which natively handle this, and those are coming and more into the play now. So with the last 2 years wherein we had this problem of COVID, it has accelerated our digital ecosystem, and then every organization is trying to become digital in its operation. Especially when it comes to education, it has taken a revolution. So all these educational services are now run into the cloud data center, and in the last 2 years, it has accelerated a lot this movement toward the usage of data center. So one of the things that has happened is that along with the changes in the organization for digitization, we also have the cases now wherein there are many startup, and startup ecosystem in India is booming. So all these startups, when they start, they can't afford to have their own infrastructure, and these data centers are helping these organizations, the new startups, to start their operation in a very small size, in a very cost-effective manner, using the instances from this data center. And then as they grow, they can buy more and more instances or virtual machines from these data centers, and then more and more workload can be put into the data center. So in many ways, data centers are becoming central to the growth of economy and technological innovation. So with the advent of data center, we also have to look at the cost, and any effort in reducing the cost in terms of hardware or software will give boom to the industry. So as and when we reduce the cost of hardware and software, it will become affordable, and it will add to the acceleration of overall economy. So in this sense, the acceleration in data centers is very important, and FPGAs play a prime role when it comes to accelerating this workload. So here also you can see a cross section of the NM1 data center, which is managed by Yota in Mumbai. So you can see it's a huge building with multiple floors, and it has halls filled with servers. So this building, along with the servers, it has also has to maintain the power for it and take care of cooling the system. So there are a big chiller system along with that. So in this form, there are multiple data centers that are coming in India now. So especially cities like Mumbai and Chennai, these are the prime target for these data centers. Along with that, other metro cities like Bangalore, Hyderabad, Delhi, these are also getting many data centers. So apart from Hiranandani and Yota here, there are other data centers that are operated by companies like Control-S, Reliance, Adani, NTT. And one of the major mention will be the NPCI, which is National Payment Corporation of India. And National Payment Corporation of India also has its own data center, and they have brought in a revolution when it comes to the financial payment using UPI and RuPay. And these are taking the world by storm. Many companies are adopting these technologies now, and data centers are playing major role in helping this application. So as we see how important the data centers are, we'll also get into the details of what happens inside the data center and each of the server racks. So if you see earlier, all the applications that used to run used to have the monolith form, wherein the users, thread, and the underlying software used to run as a monolith. But running this as a monolith has the efficiency problems. And now the trend is to go toward the microservices. So each application now, instead of having a single monolith application, it's getting into a phase wherein the applications are being constructed as a combination of microservices. So there are hundreds and thousands of microservices which run together to form an application. So here we can see more details on how the underlying infrastructure looks like. So we have the CPU racks, multiple CPUs that run the application, and then there is intricate integration of FPGAs, which have many workloads running on them, like web searching, deep neural network, SQLs, and SDN offloads. And then this entire infrastructure is connected together through the set of routers, which form the underlying network to have this connectivity in the data center. So if you get into the details of this, we can see that the set can have a CPU and FPGA in place. So for example, one instance can have just a CPU connected with network interface card, and then this network interface card connected to the rest of the system. While another systems can have a CPU along with the FPGA, which is used for acceleration, and then these FPGAs talk to the rest of the system. So along with this NIC or network interface card, now there is more and more trend to go towards smart NIC, wherein the NIC provides only the connectivity to the rest of the network. The smart NIC also take care of accelerating some of the loads, and these smart NICs contain in many ways the many types of FPGAs. So we are slowly seeing a trend wherein we are moving from network interface card to smart NIC to something called as IPU. IPU stands for Infrastructure Processing Units. So in this way, like it's slowly developing in that direction wherein the processors can be used for running the pure applications, whereas FPGA-based smart NIC or IPUs are used for running the infrastructure services. So we'll get more into the acceleration basics with this. So if you can see that each CPU here has multiple cores. So for example, the Intel Xeon CPUs come with 32 cores, 64 cores, and bigger numbers. So each of these core can run an application individually, or each core can be put it as a virtual machine. So these cores run the application from the user. Now these cores are also used to run the other services like data services or network services or security services. But any of these service that is used to run on these cores consume the cores from the CPU, and then these cores are not available to run the workloads from the user. So what it means is that some of the cores are consumed by services, and they reduce the number of available instances that cloud service provider can rent out to the customers. So this is not very cost effective because server CPUs are very costly, and any core that can be spared for the user application adds to the overall profit of the data center service provider. So there is a push now to take out these services running onto the CPU cores and move this into the FPGA or a dedicated hardware. A dedicated hardware which will be more suited to run these services. So all the CPUs that are present are generic core CPUs, and what it means is that when you are using generic core CPUs, these CPUs are not meant to run specialized loads like data services or network services or security services. So when it comes to running these services, these cores are not that efficient, and the usage of hardware or the CPU cores is disproportionately high to run these services. So what can be done is to, instead of running these services, this can be run on specialized hardware. The specialized hardware, since it is optimized for running these services, it provides the same amount of performance using the less hardware. And with usage of less hardware, it means that the cost of hardware is reduced, and also the running cost, which in terms of power is also reduced. So overall, the cost of ownership comes down with this, and that is why there is a trend now to move toward acceleration for these services. So when it comes to acceleration using FPGAs, so now you can see all the services that were running, consuming the core from the CPU are moved into the FPGA accelerator, and now all the cores are available to the user for running his application. So when the acceleration services are moved into the FPGA accelerator, what it contains is the stack, overall stack here. So the FPGA will have logic dedicated to run the user services, and then it will additionally have these data services, security services, and networking services. So overall, it can be optimized to run all these specialized loads, as well as the any specific user application that is specific to a particular cloud service provider or a particular user which is using FPGA for his application can be run here. So when it comes to acceleration with FPGA, there are two types of acceleration that we can look at. The first is called as the inline acceleration, and the second one is called as the loop-aside acceleration. So loop-aside accelerations allow for offload of heavy compute data and functions to FPGA to free up the CPU, as we saw earlier. And then there are cases wherein certain applications are very latency sensitive, and these are the applications that you want to run using the inline acceleration. So if you see here in the loop-aside acceleration, the processor is the main driver, and then it is communicating Intel FPGA to have the loads accelerated using the FPGA. Whereas for the inline acceleration, the Intel FPGA takes the central stage, and it has all the services running like network services, different devices connect to it, and also the storage area network been taken care by the FPGA here. And then CPU is free now to run the applications which it is meant for. So in this case now, acceleration provides minimal latency because it is natively running onto the FPGAs, and with that, overall efficiency of the data center is improved. So we'll, as we saw, right, what goes into the data centers and what is run into the CPU and what's run into the FPGAs. We'll see what is the FPGA acceleration is useful for. So there are many types of services wherein acceleration helps. So if you take the case of data analysis and databases, so these are hugely benefited by running into the data center acceleration. Along with that, okay, somebody is saying that volume is too low. Just let me adjust. I hope it is better now. So coming back,
Yes.
okay, thank you. So coming back to the acceleration workload. So financial services is another one. So in finance, every nanosecond matters because the data latency of the data creates advantages for the people which have less latency, and the people who have more latency will be impacted. So it's very important for financial sector. Then along with that, now there is coming the advent of network functions virtualization, or NFV. So in the earlier days, especially in the age of the network, the services were run based on the equipment provided by different service providers, and these equipments, one thing was that they were proprietary, so the cost of these equipments is very high. And at the same time, when it comes to interoperability, there are many times issues wherein if you want to run your network using equipment from different manufacturers, they don't work seamlessly. So now there is a trend towards network function virtualizations, wherein instead of using the dedicated hardware from different vendors, a set of servers can be deployed, and then virtual services can be run onto these servers. So these virtual services replace the network functions that earlier the monolithic devices used to provide. So with this, the total cost of operation for these network service providers is coming dramatically down, and at the same time, because it is creating ecosystem wherein multiple players are coming in picture, whole innovation is going to the next level here now. So the NFV is also booming in a big way, and Open RAN, or where RAN stands for the services which are run into the radio services. So radio services are getting benefited with the Open RAN. And then there are specialized applications wherein with the current advent of the communication, the users are getting hooked more and more to the video services. So services like YouTube, or movie services provided by Netflix, or other content providers. So these services also take huge workload, and specialized hardware accelerators for this media transcoding are becoming important with these video workloads. And then there is a very important issue of cyber security nowadays, wherein you just don't need to, you just don't want to run your applications in a cost-effective manner, but at the same time, making sure those applications are secured and protected from the outside attackers. So there have been many cases wherein the entire services has been brought down by attackers because the service the security was weak. So it's become very important to have a very good cyber security for the applications running in data center as well as the standalone machine. And one of the ways these FPGA accelerators are helping is basically they are providing the hardware wherein the crypto acceleration is provided into the FPGA hardware. And since they are specialized for providing the crypto services, these services are getting accelerated by the FPGAs in huge way as compared to when they are running onto the CPUs. And now we have the many companies that are getting into the artificial intelligence. So artificial intelligence in a way is becoming pervasive. So instead of leaving the business decision to the individual's discretion, there is a now trend toward developing artificial intelligence, which will process the data and come up with the models which will provide accurate predictions and will help in making better decisions. So when it comes to artificial intelligence, there is a huge data crunching that is required. Lot of movement of the data as well as the transformation of the data. And these AI workloads are also benefited from FPGAs because FPGAs are also providing specific hardware which will cater to these artificial intelligence applications. So overall, if you can see by bringing together the programmable acceleration card and the acceleration stack from the Intel, along with the FPGA hardware and intellectual properties that are provided along with these, the whole system not only helps in accelerating the application, but it also helps in bringing down the total cost of ownership. And as the new developments are happening, we are seeing much more performance per watt and performance per rupee or per dollar with the advent of this new hardware. So in a way, acceleration using FPGAs is becoming pervasive. Everyone wants to use these FPGAs. In fact, there are cloud service providers which have created specialized in ecosystems wherein they are using the FPGA exclusively for their acceleration services. So Microsoft Brainwave is one such application, and they are becoming more and more specialized using the FPGAs. And the same is the case with other data center providers as well. So now that we saw how the data centers are benefited with acceleration, we'll also see what are the options provided by Intel to help in this acceleration. So there are multiple programmable acceleration cards which Intel provides. There are acceleration cards specific to AI. There are acceleration cards specific to graphics processing. So there is a portfolio of such programmable acceleration cards. But for today's session, we'll go with the very basic pack cards that are provided by the Intel. So at the start of this range is the Arya 10 based accelerator card. So this comes as a low cost and low power deployment. So as you can see, it's a compact card and it has a PCI interface. And this PCI interface is used to plug this card into the server rack or a server machine. And then with this plug and play, the entire acceleration hardware is available to the user. So this specific Arya 10 card has 40 gig Ethernet interface, and then it has third generation PCIe interface with 8 lanes. So in the form factor, it is half length, half height single slot PCIe card, and overall it is meant for the low power applications, and total dissipated power of this card is around 66 watts. So this is at the start of the acceleration portfolio, and then the user which requires more performance and throughput can go for the static 10 based acceleration card. So the static 10 based acceleration card again is a compact card, but of course because it has more powerful hardware, it is bigger. It is a bigger form factor with 3/4 length and full height, and this comes as a dual slot PCI card. Again, you can see there is a PCI interface, which is again makes it plug and play with the server rack or servers. So it provides much more logical capability in terms of the hardware that is available on the FPGA, and it comes with a much more powerful host connectivity with third generation PCI with the 16 slots, 16 lanes, and it provides 200 gig ports to connect to the rest of the network. So these are at the very start of the acceleration portfolio. For introduction purpose, we are using them here, but you can explore the portfolio. You can go to the Intel site and check for the other acceleration cards that are provided by the Intel. So we saw how the acceleration cards look from outside, and now here are the details of the internals of these acceleration cards. So you can see at the heart of this acceleration card is the FPGA chip, and in this FPGA chip will have associated memory for running the applications. Along with that, as we saw earlier, there is a PCI connectivity. So there is a PCI interface onto these FPGAs. So which are the part of the transceivers, and then also there are transceivers related to the Ethernet. And in this case, we can see this is a QSFP plus, which is a optical connector, which are where the network is connected to this card using the SFP or QSFP connectors. So overall, this FPGA provides 1100K of logic elements, which can be used for the development of acceleration functions. And then there is a flash memory, which is available for configuration storage of this FPGA. And then we have board management controller. The board management controller interacts with the different components of board and provides configuration services as well as the management services for the entire FPGA pack card. So this board management controller is accessible to the user via USB 2.0 port for the upgradation of the firmware and any recovery that is required for the in case of any issues. So that interface is provided to the USB hub here. And overall, the power and the connections to the host happen through the PCI interface. So there are, depending on the different types of pack cards, we'll have the different power capacity that will be required by these boards. So now we'll get into more details of the software that is associated with this hardware. So here we can see there is an Intel Xeon processor here, which is connected to the Intel FPGA via PCI connectivity. The custom software is running on this Xeon processor, which offloads a competitively intensive task on this FPGA. And to leverage the flexibility of FPGA, the partial reconfiguration facility is provided. So when it comes to the AFU, to make these AFUs a kind of pluggable, partial reconfiguration capability of these FPGA is very, very important. So by using this PR capability at the runtime, the acceleration functions can be swapped in and out of the FPGA pack card or a standalone FPGA as well. So you can design multiple AFUs in the same FPGAs, and usage of these PR regions is helpful in this case. And then we have the open programmable acceleration engine, or OPA. This software is running on the Xeon processor, and then it interacts with software on the interacts with the hardware on the board through this PCI interface. So this OPA software provides libraries and drivers, and then also it provides a set of sample programs that can be used by user as a reference for his development. And to simplify the configuration process, OPA has two types of bit streams. So there are the bit stream is nothing but, so when the user creates his hardware description using the hardware description language, finally that hardware description needs to be put into the FPGA in the form of AFU. And the way to do that is basically to convert this hardware description into the bit streams. So bit streams are nothing but the configuration that will be used to configure the FPGAs at runtime. So there are two types of bit streams. One is called as the BBS, which stands for blue bit stream, and this blue bit stream is provided by the Intel, and it contains the FPGA logic to support the accelerator, including the PCI communication code, the code for CCI fabric, code required for managing the DDR memory that we saw on the board, and then management of the entire acceleration engine. So this BBS also has the PR region separated out, and then this PR region that is separated out is called as the GBS. So the blue section here is provided by the Intel, and the green part is something called as the GBS or green bit stream that will be either provided by the third party or it can be available from Intel, or user can develop his own AFU and then program into the FPGA using this blue bit stream. So this entire thing is available in the volume production, and user can integrate more and more of these pack cards as and when the requirement arises. So with this, we'll get into the details of acceleration stack that is provided with the Intel Xeon CPUs along with FPGAs. So here we can see the layers of acceleration stack that is available. So basically, as you can see, it's a collection of different components. So starting with Intel hardware. So on the top of Intel hardware, we'll have the acceleration environment. So this acceleration environment is powered by the OPA technology, and then we have a set of tools that are used in this environment for development of workloads that can be run onto this hardware. And along with these tools and the environment, OPA also provides acceleration libraries. So these libraries have routines developed which can be used by user to as the API, and he doesn't have to create each and every function that is required. So these acceleration libraries will help in fast tracking the performance of the application. And then there is industry standard framework that can be run along with this stack. So once this is available, the user can use this infrastructure to create his application development, and then deployment can happen at the rack level. So this acceleration stack also has support for OpenCL. So for the developers who need to create custom acceleration functions, the acceleration stack provides SDK for OpenCL. And not only the application be developed by using OpenCL, but there is also support for traditional RTL development. And then using this RTL development, user can fine-tune his applications to take advantage of the underlying hardware. So overall, if you can see, the acceleration stack simplifies development of the user applications, and it helps in performance enhancement of these applications. So with it, now we'll go into the details of this acceleration environment. So we saw overall where the acceleration is useful, how it is divided into software and hardware, and the different components of the system. So we'll now get into more details of this acceleration environment. So at the heart of this acceleration stack is the acceleration stack that we saw in the previous slide is this acceleration environment. So here you see CPU on the left hand side and FPGA on the right. So goal of this system is to provide user application running onto the CPU to take advantage of the FPGA acceleration function. So the AFU can be created by the developer for his applications, and then this AFU will run into the FPGA. So once this application is running into FPGA, there needs to be connectivity between CPU or the host and between this FPGA. And the FPGA interface manager or FIM provides this connectivity between the FPGA side and the CPU side. So with the use of FIM, standard PCIe or UPI high-speed interconnect can be used to connect the CPU with the FPGA. And with this, it simplifies the overall connectivity, and this is taken care by the software stack, and user doesn't have to worry about his communication. So purely based on the requirement, user can focus on to his development of his workload or his applications, and then underlying communication and other requirements are taken care by the software stack. And the advantage of this AFU is that once user develops the code for this AFU and his application running on the CPU, the same code can be run on to different flavors of FPGA flavors that are provided by the Intel. So developer can take advantage of these acceleration libraries overall to fast track their application and then reuse that application into different platforms. So if you see from this diagram, the key to make the whole system work with the FPGA hardware and CPU software is to take advantage of the Opa APIs and then use this Opa technology to interact with the FPGAs to fast track the applications. So now we'll get one more into details of what is there as part of these FPGAs when you are using it for the acceleration stack. So on the FPGA, there are components that enable communication with the CPU. So communication happens with the PCIe, and then FPGA interface manager provides the layer between PCI side or the host side and on the other side it connects with the AFU. And the connectivity to the AFU happens through FIM, and FIM takes care of handling of translation of commands and commands from the host, and then also providing responses to the host. So along with this FPGA interface manager, there is a protocol engine, there are caches, address translation, and other logic to make this connection possible. The FIM is connected to the user logic through a protocol called as Ccip protocol, which stands for Core Cache Interconnect. And this interface is must in when it comes to the development of AFUs using Intel FPGAs, because with this core cache interface, it provides a standard interface to the software side, and the software can be can run on different FPGAs when the components are created using the core cache interface. So there is also when you are designing these AFUs using OpenCL flow or RTL flow, as we said, we need to conform to this CCIP interface, and entire AFU is located onto the FPGAs in the partial reconfiguration region. It allows FPGA hardware to reconfigure the AFU bitstream accelerator functionality. And when using discrete FPGA on a PCI board, the AFU will also have access to the external memory controllers, which can be connected to off-chip DRAM memory that is a standard memories that are available in the market. So now we'll get into details of hardware and software co-design approach that is required to make the application successfully deployed onto these FPGAs. So there are two flows for AFU applications. There is OpenCL based, and then there is a RTL based flow. So for our today's session, we'll focus on RTL based flow. So you can see on the hardware side, FPGA IP development uses the same Intel Quartus Prime software that is used for the traditional FPGA development. And on the software side, programming of the CPU is taken care by the OPA APIs. And to facilitate this functional verification, Intel also provides the ASE, which stands for simulation environment, AFE simulation environment. So what happens is that as and when in the real application, the OPA layer will be talking to the AFU running on the hardware. But if you are when in the development phase, if you try to do these, there can be many issues in the code, both in terms of software code and the hardware RTL that is developed. So if you try to run this application, this environment, it can be very tedious to debug these applications. So Intel provides this ASE or the AFE simulation environment, which can be used to simulate the hardware and software flow, and which will help in enhancing the development or fast tracking the development, as you can run multiple cycles, debug your applications, and once it is hardened and you have the confidence, then you can port it to the actual OPA platform using the FPGA pack card or FPGA. So we'll get more into the details of connectivity between the AFU and how the RTL AFU is connected together. So as we saw earlier, the accelerator application developer if he wants to have absolute control over the FPGA IP and also have the FPGA development expertise, then RTL AFU development flow is ideal for developing these applications. In this flow, we'll look at the application where user focuses on development of AFU using these behavior languages such as VHDL or Verilog and Quartus development software to use these created RTL. So the user has to ensure that RTL supports the core cache interface standard, which interfaces the AFU with the acceleration stack to a part of FPGA interface manager on the FPGA interconnect. So CCIP it's a memory-based memory mapped interface that supports simple read and writes. And then the interfaces uses these physical addresses and also this request has use a tag match responses. So there is no guarantees when it comes to the order of responses that will be sent back. So this type of minimal requirement interface actually satisfies majority of algorithms that are applicable for this FPGA. So for example, you can have the double buffer kernels that read from and write to different buffers. And more importantly, it can also support streaming of kernels that read from one memory map FIFO and write to the another FIFOs. So we'll get here, we'll understand more details about the CCIP protocol here. So there is, of course, there is a specification available. You can check on the Intel site to get the more details of the CCIP interface. So, but for the purpose of these sessions, we'll get through the major features of this protocol. So this protocol itself just handles the reads and write. The cache line reads and write are also supported. And all of the addresses coming through the interface are physical addresses and have a unified address space with Xeon CPU that is it connected with. And CCIP is a split transaction protocol. This means replies are separated from its associated request, and the responses are only matched to the request using a tag in the protocol. So the matching should not be done based on the ordering because there are no ordering guarantees. For example, write may bypass other writes even if they are to the same address. So user have to be careful about this. And if you need higher level memory semantic extensions, those features can be built on the top of CCIP through the instantiable SIMs. So Intel supports those SIMs, and you can approach the application engineers to get more details about that. So yes, as I said earlier, if you need more details on this CCIP interface, please look at the CCIP specification available at the Intel site.
Nilesh, there is a question in the chat.
Yeah.
So the question is it possible to use FPGA to render 3D real-time ray tracing rendering for CG and game development? Do we have any specialized FPGA for that?
Yes, I mean, we have the generic purpose FPGAs, but user can develop his applications for this purpose. And we are also coming up with the support systems now, wherein graphics processing will be provided as the hard IPs, and those are the new developments that are happening. And with those hard IPs, user will be able to process these graphic loads and you'll be able to accelerate these applications. Any other questions?
No other questions. You can continue.
Okay, thank you. So we'll get into the details of this CCIP signal mapping. So here you can see CCIP signal mapping is used to connect FPGA Accelerator AFU with the rest of the system. So first we see the request and response signal associated with the channel 0. And these include request memory header and response memory header. So these are all the details of these signals that are pertinent to the CCIP. So on one side we have this request, on the other side we have the response. So these are the request related signals, and on the other side we have the response related signals. So channel 0 also supports the MMIO mapping. So for the transactions which will control the AFU. So here we can see that channel 0 request MMIO header along with the response MMIO header, which is assigned to channel 2. And finally, here we also see other signals related to clock, reset, error signaling that are connected to the AFU. Because there can be conditions wherein AFU directly want to provide the information about certain error states that are happening inside the AFU logic, and this can be this information can be provided to the host side through these error signals. So again, to get the more details of the CCIP, please refer to the CCIP specification. So till now, yeah, we have got into details of hardware, and now we'll be looking on the software side of the stack. So as mentioned earlier, this software stack is called as the Opa software stack, and the software interface is through this Opa software stack that will be used to connect with the host side. So what is Opa? It is the collection of the software components and APIs that simplify and streamline the integration of programmable FPGA into the applications. So this Opa consists of a set of drivers, user space libraries, and a set of tools to discover, enumerate, and query the AFUs that are developed on the FPGA hardware. So there are many advantages of using this Opa platform. So first of all, it provides this consistent API wherein same set of software that is developed can be used across the product generations and platforms. Another thing, the advantage with Opa is that it's a ecosystem which is open source. So and it uses the BSD license. So all the advantage of open source development is available with the Opa. And then Opa technology also supports not only the a bare metal operating system, but it also supports the virtual machine. So just to provide little detail on what is the bare metal operating system and virtual machine and what is the virtual machine. So a typical deployment of the operating system happens on the hardware directly. So if you take your, for example, your home desktop, or you take example of the laptop, the software is directly running the operating system, for example, a Linux system or a Windows system is directly running onto the underlying hardware. So these systems are called as the bare metal operating system, wherein there is a direct connect between the operating system and hardware. And then when it comes to the especially into the data centers, because there are multiple cores available in the CPU, you want to use those CPUs for different users and different applications. So there is a lot of power available within a single chip to support hundreds and hundreds of users and their application. So in this case, to create that separation between the different users, different machines, so the hypervisor is used to talk to the underlying hardware, and then this hypervisor provides interface to the guest operating system. So in this case, now these operating systems will be running onto this on the hypervisor, and then multiple instances can be created, and each of these instances can work as a separate machine, which can be dedicated for different applications. So OPA supports both these bare metal operating system as well as the operating systems running on the virtual machines. The underlying stack will take care of supporting both these systems. So this OPA technology is fully compatible with AFU simulation environment. So what it means is that when you are running actual applications into the FPGA, you'll be running it in actual hardware, but when it using for the simulation purpose, the same OPA stack will also facilitate the connectivity with the simulator that is being used for running the simulation. So so along with these different aspects of OPA, which help in connectivity between software and hardware and development of both user hardware and user software. This also provides guides, command line utilities, and sample code that can be used by user to develop his applications. So to get more details, please go to the 01 org. And now this 01 org is moved to the GitHub. So using the standard GitHub interface, you can get access to these OPA software libraries. So getting into the details of this FPGA driver, we'll look into the different components that are available. So we have kernel space and user space, and this entire FPGA development FPGA drivers sit during this user space and the kernel space. So the FPGA driver architecture sits below the OPA layer in the FPGA driver. So here we can see that interfacing with the FPGA is the FPGA driver, and then OP library interacts to driver with the using kernel space with the FPGA hardware. So when it comes to the non-virtualized environment, the host interacts with the FPGA to just the physical function. And in case of a virtualized environment, the driver uses the SRIOV mode. So SRIOV stands for single root IO virtualization, and this is the virtualization technology that is provided by the Intel. So using IO virtualizations, multiple virtual machines that are created can interact with the underlying hardware seamlessly. So the same set of hardware will cater to all the virtual machines running on the CPU, and it will provide the seamless interface for the operating system. So operating system doesn't have to deal with separation of hardware concerns. It is totally taken care by the software layer that is provided through the SRIOV by the Intel software stack. So you can see the driver here is divided into 3 parts. The first part is the FPGA management engine driver. So it stands for the short form is FME, FPGA management engine, and this driver is the first component which is part of the physical function. And this FME handles tasks such as thermal and power management, reconfiguration, debugging, and error reporting of the hardware. And then there is a AFU driver which exposes 256 KB regions as control registers, and it allows users to actually control, operate, and share memory buffers with the AFU on the FPGA. And then finally, we have the ports, and each of these ports attaches to the AFU. So there may be multiple ports, so each port can be assigned to a different virtual machine here. So each of the all these ports facilitate the interaction, and overall you can have the communications to multiple ports and create your AFU to have these different ports available. Now that we saw the different components, we'll get through the details of this library at a glance. So you can see the OP library has these multiple components, and overall it is a very lightweight library which will be further extended in the future. The core library has these header files along with the runtime libraries, which are the SO files for the application use. And we also have the alternate implementation, which is the AFU simulation environment, and there are also related files, SO files related to this ASE environment. And then along with these libraries, we also have a set of tools which provide help with different tasks, wherein you require to do the partial reconfiguration, diagnostics, and then monitoring of the system. So all these tools like FPGA Conf, FPGA Info, FPGA Daemon are used for this purpose. And then along with this tools and libraries, we also have a set of documentation that will help in development of the overall application. So currently, the OP library it provides C APIs, but there are plans wherein the work in development, wherein other languages will also be used to provide these these APIs for the usage with other development environments. So overall, we see that this library provides a common development environment, and then using a set of tools, libraries, applications, and documentation support, the user can greatly enhance his development of his AFU. So when it comes to the user development to OP, there is a C software library that is available. So first of all, the user application needs to include this fpga.h header file. And this header file is the only one that requires to be used in the user application. So in this case, you see this myapp.c, and it can be for you, for example, if you are doing, let's say, graphics processing, then you can call your graphics app.c, and that can include this fpga.h file. And this fpga.h file then has a set of other header files that are required for the development. The user application can link against these libraries and use these in application. So this OPC code library this interacts with FPGA hardware drivers, while the ASC library provided here interacts with the simulation environment and RTL simulator. The two libraries, one for the actual hardware and one for the simulation environment, these will help in both the flows, for RTL flows as well as the flow with using the hardware. So these APIs are implemented differently for RTL simulation and for the hardware. But from user point of view, all that it needs to take care is include this FPGA.8, and then underlying libraries take care of handling it separately for simulation environment and actual hardware environment. So user doesn't have to understand the details of how the underlying details are taken care by the these APIs, and user can focus on his application development. So now that we have seen what are the different components available in OPA, we'll look at the programming model of the OP. So the overall programming model of OPA is based on the object. So this object-based model simplifies and abstracts the actual FPGA hardware. So details are hidden behind these objects. So user needs to just deal with the objects, and he doesn't have to get into the details of underlying infrastructure. So the first object here is the properties object. User needs just to this properties object, which will be used for matching of the FPGA resources. So with the properties object, user can fill in the requirement of FPGA resource. So each AFU and FPGA have its own properties, and these properties objects map to those properties of individual AFU and FPGA. The properties object is used to filter, to discover and search for the matching resources. And once you find out the matching resources using this properties object, and that meets your need, then this properties object will provide a token object. And if the token is valid, then the resource you're looking for exists. So before using a particular FPGA resource, you'll need to acquire the ownership, and use of token object to acquire ownership of the resource. If it is successful, the function will return a handle object that signifies ownership. And once the ownership is acquired for the resource, then we have the handle object. So ownership of AF resource may be shared among multiple processes, or it can be exclusively used by one process. So after acquiring the ownership, here are some of the common tasks that you want to perform. So you can map the AFU control register to the user virtual memory. This is the control mechanism of AFU functionality, where you read and write to the memory addresses to control the AFU. You can also share the memory. To do this on the CPU side, you can allocate memory and map it to the AFU, so the memory can be set up to be shared. And then we can invoke the AFU by issuing commands such as start, stop, pause to control the AFU registers. And once the execution is completed and the results have been utilized, then a deallocation of the memory can happen. So here we'll get the another look at the object model. This presents a very simplified picture that we saw in the previous slide. So you can populate the object properties using the FPGA properties API call. And then once that is done, it will provide the query to the resources. And once the resources are queried, then you can look to populate it for your FPGA application using the properties such as socket or bus or the query of the item number. And if this is successful, then you receive a token which identifies that particular resource is available which you are looking for. And then finally you get the FPGA handle, which signifies the ownership of that resource for your particular application. And once this ownership is successfully achieved, then you can use this FPGA handle to carry out the further tasks that are required by your applications. So once we have this handle, we'll get into the enumeration and discovery of the resources. So let's examine this into more detail. So first we declare this FPGA properties called prop, and then we also define FPGA token called token, and then we use the GUID called my GUID to identify a particular AFUID. So in this case, you can see there is this particular AFUID, which this my GUID will point to. So once this is done, we can use the get properties to fill in the appropriate field for the properties of the object. Next, we use this set object type call to set the properties to be used for FPGA Accelerator, and then we use the set GUID for that resource using those properties. And finally, we have the object called properties object called to set appropriately, and then we can use FPGA enumerate, and it will return a list of tokens that correspond to the resources. The enumerate call searches the resource within the current environment that matches the properties that has been passed into this call. And if those properties are found, the call will populate the token. And it will also, there is another parameter which are the num matches. So there can be multiple matches, and you can restrict how many matches are considered for this token. So that is specified by these num matches here. And once you have this token, we can call the destroy properties. So destroy properties will free up the property object if the properties are property object is no longer required by the application. So this is how the enumeration and discovery happens for the resources that are available with the AFU. So there is a note. So every function returns the error code. So anytime you are using these APIs, it is suggested that user applications look at that error code and make sure that there is no error before proceeding to the next step. So that is very important, because if there are any issues and the error codes are not taken care of, there can be issues in the further processing of the application. So
Nilesh, there is a question in the chat.
Yeah. I cannot see Padmanabhan. Can you tell the question?
Yeah, sure, I can tell that. Yeah. Is it used to print the simulation results that are reported from the simulation modules? What type of parameters are we targeting? Please clarify more.
So this is in the ASC environment. In the ASC environment that we need the debug. Okay.
Yes, yeah.
So when it comes to the ASC environment, a standard display function or the monitor functions that are provided with the provided by let's say the Verilog RTL, right? Verilog language can be used. So user can have this print statement or display statement within his code, And as the simulation runs, this stateless statement will be will output the whatever the user log or user information related to his the values or different signals or any monitoring of any objects within the code, and that will be logged into the user log. User can then look at those user log and check for the particular messages, and then based on the messages, user can go about debugging those applications. So that is how you handle it. Any other question?
Let's know that we can continue.
Okay. So here we are getting into the details of the code. So here we can see how do you acquire the resources, and after you have done that, then we use this token from the this acquisition of the resources that was obtained through the enumeration, and then we create an empty handle. So this empty handle will be passed to the FPGA Open API here. So FPGA Open API is to acquire the resources, and using this token, if it is successful, the handle will be filled with the valid data. And once you have the valid handle, you will be able to do the useful things with it, as we discuss going forward in the slides. So once you have finished with the FPGA resources, then the FPGA close call can be used to release the handle object. So even when handle becomes invalid, the token still remains valid, and that can be used again if there is a requirement to use that token. So as we saw, between acquiring and releasing of the FPGA resources, you also be invoking the FPGA AFU. So once you acquired the resources, you invoke the AFU, and once that is done, then you go and relinquish your resources. So FPGA map MMIO is the API. This API call maps the FPGA AFU control register to the software process virtual space. And then this call goes through the library and talks to the drivers to take care of the different tasks. And when finished, a map pointer will be returned, called this MMIO pointer. And through this pointer, you'll be able to read and write control registers using FPGA read MMIO and FPGA write MMIO call. So here we'll get into the detail of the memory mapped IOs that we saw in the previous slide. So here you can see we are defining a pointer, and then we are using the 64-bit calls here. So we are defining the 64-bit properties for the handling of this accelerator. So here you can see the code that uses the FPGA map MMIO. This call takes handle, and then it returns the pointer, which we have defined here. And then this pointer points the mapped area within the FPGA. And with this pointer, you'll be able to do then perform the reads and writes to the FPGA AFU registers. So these calls can be both 32-bit calls or 64-bit calls. And in this particular example, we are using 64-bit call. So we have this FPGA write MMIO 64 for that purpose. So in case it is a 32-bit call, then it will be FPGA write MMIO 32 and FPGA read MMIO 32 in those 32-bit applications. So once we are done with this application, then we can unmap the accelerator using FPGA unmap MMIO. So this is how the life cycle of AFU goes. And once that is done, we can move on with the another AFU in the same user space, in the same FPGA user space. So we saw that in the previous slide, we have the memory mapped IOs. So along with these memory mapped IOs, we can also use shared memory. So let's say the memory that is available with the FPGA is not enough, and you want additional memory. So in that case, shared memory can be used from the host, because typically the host will have huge memory available with it. And in this case, the usage of system memory for FPGA Accelerator will enhance the utility of the application. So when you want to use the shared memory from the host, we have to keep one thing in mind, that FPGA only understands these physical addresses. So there is a need to translate the virtual addresses, because typically the host side, everything is dealt in the virtual addresses. So we need to do a mapping between these virtual addresses and the physical addresses that FPGA understand. So the FPGA prepare buffer is the call that is used. It is a library call that does this. So using this FPGA prepare buffer, we'll be able to map a virtual memory to the physical memory. And if, let's say there is a particular usage scenario wherein you want to specify what is the amount of memory that you want to specify that is required by the FPGA. So the parameter for specifying that is the len. So based on this len value, the host will set aside a set amount of memory that will be available to the user. So there are two cases. So let's say the host has already, so let's say you are starting from scratch. In that case, we use this FPGA prepare buffer, and based on this call, the memory is allocated by the host. Now there can be a case wherein you are running another AFU and host has already pre-allocated the memory based on your previous call. So in this case, we can use the pre-allocated memory, and when we need this pre-allocated memory, we need to pass this FPGA buff pre-allocated parameter to this FPGA prepare buffer call, and in that case, the pre-allocated memory will be available to the FPGA application. So one thing to remember in all this is that whatever the memory that is allocated for FPGA use has to be a physically contiguous memory. And the OPA library API will make sure that host is providing a physical contiguous memory which is mapped to the FPGA application. So user doesn't have to really get into understanding how the physically contiguous memory is allocated, because that is all taken care by the OP library. So as with the previous example, now we'll get into details of how the code looks like when you are trying to do the shared memory. So here we ask the library to allocate the memory using FPGA prepare buffer. So the last 0 here in this argument list is the flag that indicates that it has to be created and create the memory. So this function will return buffer pointer for the memory that is allocated. And next, we'll use this to do the translation between this physical address that FPGA Accelerator understands. So to do that, we use this FPGA get IO address, and this call will return the physical address that can be used by the AFU present in the FPGA. And once this is done, then the same set of memory is now shared between the AFU and the processor. And after that, once all the tasks are completed, we are now ready to release the memory back to the host. And to do that, we use this FPGA release buffer call, which will deallocate the memory and it will be returned back to the host. So as we saw earlier, there are two cases. As we saw previous example, wherein we were allocating the new buffer to the FPGA side. Now there is a case wherein already a buffer is allocated, and this example code goes through that. So it is very much similar to the previous example. The only difference here is that the FPGA prepare buffer call needs to be passed this FPGA buffer pre-allocated parameter. Once that is done, the rest of the processing is same as with the previous example, and then again the memory becomes available to FPGA. And after all that, we can release and deallocate shared buffer using this FPGA release buffer. So till now, we have covered a main step on how to use the FPGA. But what if we want to change the AFU functionality? So let's say you have one AFU and now you want to use another AFU by replacing the existing AFU. So how do you go about that? So this management and reconfiguration section will get into detail about how to changing the functionality of the AFU. So to load new function, you need a new GBS. So as we talked earlier, GBS stands for green bit stream. So this is the user application. So user application is created, the RTL code is ready, and then that code is translated using the Quartus tool into a bit stream. And that is what you are referring to here as the green bit stream. So this green bit stream will contain the new AFU. And then we can load this new GBS file using the FPGA conf command, and this will be loaded into the FPGA using the underlying library calls. So this underlying FPGA call here is the FPGA reconfigure slot. This will go through the drivers and then it will perform the partial reconfiguration of the FPGA and then reconfigure the partial reconfigured region for this new AFU functionality. So here again, we'll look into the code that is the code required for performing this allocation of the new AFU. So again, to do this, you must have the appropriate privilege that is high enough to have the FPGA management functionality. And here we use fread, that is nothing but a file read, to read the GBS file into the software, and then using the GBS pointer, it will be the software will have access to this GBS file. And after that is done, we use this FPGA reconfigure slot handle to program the new GBS or new AFU into the FPGA accelerator. So with this, the new AFU will take care, a new AFU will occupy the existing configured PR region, and the new functionality will be enabled. So once we have these AFUs configured into the FPGA, then we need a set of tools that are shipped with the OPA, which will help in diagnosing and testing of the FPGA hardware, and also to do the interesting things that the user application wants to do. So here are the set of tools. So first is the FPGA conf. So FPGA conf, all these are command line calls. So FPGA con is for the reconfiguration of AFU using the API. And once we have this FPGA configuration done using FPGA conf, then we can use the FPGA diac to perform the diagnostic and testing of the FPGA. So it takes different arguments, and depending on the value of argument that is passed, it can test loopback functionality. It can do bandwidth and latency measurements and other characteristics that are based on the parameter passed. And then FPGA info is the command that is used to report back the status of the FPGA. So different parameters such as temperature of the components, errors, and power status can be reported using this FPGA info command. And finally, we have the FPGA daemon. So FPGA command runs a daemon which does the monitoring of FPGA drivers, and if any error in the driver status, it will be reported by this daemon. So all these tools are shipped along with the Opa library and available to user from the command line. So as we saw earlier, we know now what is the pack card and then details of hardware and Opa software library. And with this understanding, now we can get into the development flow using the RTL simulation. So with the RTL flow, it is important to take advantage of ASE, which is AFE simulation environment, because this is the flow which will help in easy diagnosis development of the RTL code. So the simulation environment supports both the Opa software layer on the software side and CCIP protocol on the AFU side. So with ASE, user can verify Opa software together with the AFE RTL without being actually having access to the FPGA system. So this runs parallel to the FPGA system, and once the development is done, the user can run the same software and bitstream generated from the RTL on the hardware system. So software application in this case simply loads the ASE library which supports this Opa, and then automatically connects the RTL simulation using the system Verilog DPI. So there is no different from user's perspective whether it's running on the actual hardware or it's running on the RTL code, because that transparent access is provided by the Opa here. And when it comes to executing on the hardware, the application simply changes the link library to the runtime library, where RTL is compiled by quarters into FPGA bitstream, and the same source is used as the source code is used as that was used in the simulation environment. So here we'll see more detailed feature and what are the different feature as well as the limitations that are coming from the ASE simulation environment. So the ASE is a transaction level simulator. What it means is that the models, the AFU in this environment models the CCIP transactions. So all the abstraction happens at the CCIP level, and we cannot look at the signals that are below the CCIP level. So that is one of the important thing to be noted here. And ASE is also capable of identifying CCIP protocol correctness. So if any issues in the CCIP transactions, that will be reported by the ASE environment. So Essentially, this AAC environment translate your OPI calls from application software to CCIP transaction and then simulate them in the simulator. The execution of this AAC does not require any administrative privileges, but it requires a 64-bit simulator which supports DPI calls. So it can be either any of the simulator like Synopsys VCS or QuestFacil. And then when it comes to the limitations, yes, there are certain limitations. Since it is a transaction simulator, it is not cycle accurate, and it cannot be used for the performance measurement. It also is not a cache simulator, nor does it have any latency modeling done correctly. So what it means is that once you have coded this RTL, it doesn't guarantee that okay, it is synthesizable code or it will be able to meet the timing. So to make sure that this code meets the timing and synthesizability criteria, again you need to take this RTL code through Quartus tool chain, and only when it passes through the Quartus tool chain, we can guarantee that okay, this is synthesizable and it will meet the timing requirements that are required for a particular FPGA family. So here are the steps that we utilize for AFU simulation environment. So there are certain set of variables that needs to be set for this environment. So for example, if you are using a VCS simulator, then we need to set VCS home variable. And then we also need to set Quartus root dir and QCS home, which will be utilized by the Quartus for linking with the underlying libraries. So all the simulation scripts are located in this location. So whatever the hardware directory you have, within that you have the green bits example, and within that source sim directory will contain all these scripts. And to run simulations, there are handy utilities that are provided. So using the setup_sim.sh and run pp.sh, all the simulations can be run. So the next step in this process is creating the blue bit stream that needs to be programmed in the AFU. So once we have this AFU verified in the AAC environment, we want to use the Quartus Prime tool to perform synthesis, PNR, and timing closure, and then use this created bit stream for the AFU. So again, this is done through using the run.sh command. So this script takes care of all these above steps. It will create this compilation of the AFU, and then it imports the FPGA interface manager database from library as part of a partial reconfiguration, and to generate the partial bit stream. So if you need the examples to start with, Quartus projects can be found in this particular directory. So OPA platform root will be set by your administrator for your system, and then you can look at this location to check for the AFU applications. So there are 3 revisions available, and each of these revisions in these examples provide certain functionality. So the first one is the AFU synth, and this revision is used to synthesize the user AFU. And when it comes to the fitting it into the FPGA, we have the pre-fit AFU and the post-fit AFU. So fitter will do the place and route synthesis, and then once all the stages are passed, we have the post-fit AFU, and that will be the part of this AFU fit revision. So along with that, we also have the DCP revision, which is used to integrate AFU with the FPGA interface manager. So you can look at this Hello AFU example in the AFU developer guide to get more information about creation of the bit streams. So how do you prepare the design for debugging? So the tool provided is the signal tap logic analyzer, and using this signal tap analyzer, we can get more insights into the design for understanding the different parameters of the design. So to prepare the design, you need to follow these steps, and once these steps are followed, you will be able to debug your design when it is running, the AFU is running on the FPGA chip. So first, open the AFU scene revision that we discussed in the previous slide. Open it in the Quartus software and run analysis and elaboration. Next step is to set up the signal tap by creating a file in the signal tap GUI. Add nodes for the tap, set up the trigger conditions, and other possible options that can be used by the trigger hardware to capture the signals. And in the Quartus setting, we need to do this setting up of the parameters. So these three requirements, these three settings are required for the signal tap analyzer to work. And after the compilation is done, which will generate the AFU bit stream, and then this bit stream can be loaded into FPGA, and it will enable debugging of the hardware as it runs into the FPGA hardware. So once we have put the bit stream in place, we can start this remote service on the host machine using this mmlink command, and then we can copy these files into the working directory of remote machine. And once this is done, we can start the system console for remote debug using the system console command. And once we have this GUI coming up, then we have to wait for this remote system ready, and then open the signal tap and connect to the hardware. And once the connection is done, then we can go about debugging the AFU in the running into the FPGA using the signal tap analyzer. So here are references to the quick reference guide. So till now we talked about different steps and commands to create the create and run AFU. All as a quick reference guide, here are some of important things to know. The utility to program AFU AFU bitstream into the FPGA is FPGA COM, and you need a system privilege to use that command. So once you have the system privilege, bitstream can be programmed using FPGA COM. And to build examples of design software, simply use the make command after you have pointed out to the compiler to the OP location that is set by using this OP platform root variable. And to run the design application software, we need to set the LD library path to the library location of the software, and then run the Hello AFU program using again the system privileges. And finally, here is the script to compile the AFU and required for the our AFU application. So with this, we come to the conclusion of this presentation. To summarize, we went over the flows and tools necessary to successfully develop AFU for the acceleration stack. And then the AFU RTL needs to conform to the CCIP standard. So that is very, very important, because without this compliance, OP software stack will not work with the AFU that is programmed into the FPGA. On the software side, use of Opa API layer to communicate with the AFU is what it will do is that it will abstract away all the driver calls as well as the FPGA interface hardware that is present. And to test the AFU before availability of hardware, we use the ASE or AFU simulation environment, which can be used with the same source as the production RTL and host software. And finally, you can follow the example scripts to create the AFU bit stream, and as well as to create the debug capable bit stream that we saw with signal type analyzer. So here is a set of references and documentation. So it provides a list of quick start guides that will help in creating this AFU in the simulation environment with the FPGA acceleration stack. And also here's a CCI specification reference that will help in creating the AFU as required by the Opa stack. So one of the very important resource is the 01.org, and again it is present in the Git library. So also there are different trainings and talks available if you need to further explore FPGA acceleration with the Intel FPGA hardware. So with this, we come to the end of our presentation, and I'm ready to take any questions along with Padmanabhan, if there are any final questions. Thank you so much.
Thank you so much, Nilesh. Thank you for a wonderful talk, and I hope we have answered all the questions. There are no questions in the chat. You can wait for a minute, Nilesh, and then.
Sure.
Thank you, Nilesh sir, for now. The next session will be taken by Padmanabhan sir.
Right. There is a question, Nilesh. Can you tell more about VMs on accelerators?
Okay, so VM stands for virtual machines, and as we saw in the earlier slides, basically virtual machine provides similar functionality to the physical machine or the physical desktop environment that user sees. But under these virtual machines, there is a hypervisor software that is running. So this hypervisor software provides the layer wherein multiple guest operating systems can run on the same CPU processor. So each of the CPU processor we saw, like the Xeon processors, right, which has multiple cores present in that. So it is a very powerful CPU, and compared to a desktop CPU, there are a lot more cores available to execute any workload. So when it comes to the data center, people prefer using these Xeon CPUs, which have multiple cores, because one advantage of that is that instead of using multiple client CPUs, you can use one powerful CPU, which is a very cost optimized solution, which provides power equivalent to multiple client CPU cores at a very reasonable price. So using that advantage, you use a powerful CPU, and that powerful CPU now, along with the hypervisor and multiple guest operating systems that are running, can use that CPU as a virtual machine. So for example, if you, let's say in your house you have 4 different desktop or laptops, there is no need to have individual hardware for that. You can run that one CPU in one server rack, and then you can create virtual machines on that server rack, and then each user or each member of the family can create his own virtual machines, and it will look like to each of the user that he's running his own CPU. So underlying hypervisor will take care that all the hardware, for example, the disk drives, the network connection, it is shared between these machines. And from the software point of view, it looks like as good as a independent is hardware to each of the user. So so acceleration with FPGAs works on the bare metal. So bare metal meaning the machines which are the independent CPUs present for them, or it works along with these virtualized machines, which are multiple virtual machines or the virtual desktop system or a laptop system, right, are running into a single hardware machine. So irrespective of whether it's bare metal or VM, the flow remains same. Underlying OP software takes care of abstracting that. And from user point of view, there is no difference whether it's bare metal or it is a virtual machine that is used for the acceleration.
The resource management of each VMs flexible?
Yes. So that is taken care by the underlying hypervisor. So for example, nowadays, right, there are also coming the concept. So till now we used to have the each server rack containing its own disk drives, containing its own network. So now we are slowly moving toward data centers which are composable, which are called as the composable data center. So in this case of these composable data centers now, the concept of having a single server is going away. So basically all the resources when it comes to memory, hard disk, or even the CPU power doesn't have to be physically present in one single machine. And this further enables scalability. And when we have such a scalable solution, definitely it brings down the cost. Because what happens is that when you have one physical machine, the memory is dedicated to that machine. So let's say you have 10 machines, out of which 2 machines require a huge amount of memory while other machines are not using that memory, then that memory goes unutilized. But when it comes to this composable hardware now, the memory, there is a common pool of memory that is created. And then using the hypervisor or underlying virtualization software, all the machines can get the allocation of this memory based on their requirement. So this brings in efficiency because earlier, whatever the independent server machines were not using the memory, now that cost is covered by the single pool, and you can have a small common pool compared to the aggregated total memory of different machines, which will cater to all the needs. And as and when the user needs memory, he can use it and then relinquish it back to the pool. So similarly, the case for computing resources, and similarly the case for hard disk drives. So all this is slowly become a reality, and we are getting into the phase where data centers are becoming this set of combination of composable hardware as well as the composable software using microservices.
Thank you so much, Nilesh. There are no other questions.
Okay, thank you so much, sir. And thank you everyone for attending and asking those wonderful questions. I hope this session has been useful to everyone. Thank you so much. And we can move on to next session now. Thanks.
Yeah, thank you so much, Nilesh. Thank you so much.
Thank you, Nilesh.
All right, so let us move on to the next session. We can discuss on the FPGA simulation and debug. I'll start sharing my screen. Please confirm whether you're able to see that.
Yes,
Visible, sir.
All right, yeah, thank you. Right. So we have discussed about introduction to FPGA simulation and debug in the earlier session. So what are the things that have been covered and then what we are going to discuss now? Let us get into the details. The objective is to understand and select and appropriate debugging tools for FPGA designs. So what we have discussed earlier, we used Model Sim Intel FPGA Starter Edition tool. And on the actual hardware, we discussed on the signal tap logic analyzer as well as the system console. So the focus of today's session is to understand about the Questa Intel FPGA Starter Edition and how we are going to perform a specific kind of applications related to assertions and coverage. So I will just walk you through the demo and we can have the Questa Intel FPGA Starter Edition tool that can be installed and that is available with the Lite Edition itself. So that is the last session in the simulation and debug. We had 4 special sessions in simulation debug. The one is the DESIM simulation tool. The second one we discussed about the signal tab. And the third one we discussed about the system console. And now we are going to discuss about the Questa Intel FPGA Starter Edition software. What is this Questa Intel FPGA Starter Edition? So we will discuss more about this in detail when I show demo about the tool and what are the different things that need to be taken into account. Both Questa Intel FPGA and the Questa Intel FPGA Start Edition, right, are a version of Siemens EDA Questa core software targeted for Intel FPGA devices. The greatest advantage is it is getting supported in Lite Edition, Standard Edition, Pro Edition, Intel High-Level Synthesis Compiler, Intel One API, and DSP Builder for Intel FPGA software. The greatest advantage is it supports Lite Edition. Therefore, along with the Lite Edition software, what we have where we used Model Sim for Intel FPGA Starter Edition examples, we can also install Questa now and perform system Verilog examples. So it supports all Intel FPGAs and Intel Max CPLDs and Intel gate level libraries, which includes behavioral simulation, HDL test benches, and ticket script. So let us get some details about the Questa Intel FPGA Starter Edition, and then we will move on to the presentation slides again. So if you just get into our details, like you can see here, Questa Intel FPGA Starter Edition. This will take to our page where we can get more details about our Questa Intel FPGA Edition software, where you could see that this is supported for all Intel FPGAs and Max CPLDs. And you can see there is a start guide that will help you to review the details of the Questa Intel FPGA Start Edition tool. And the Questa Intel FPGA Edition software replaces Model Sim Intel FPGA software. That means you don't want to use Model Sim, so that you can use the Questa Intel FPGA Starter Edition only for performing our simulation. And the greatest advantage is like it is up to 2.5x faster than our Verilog or VHDL simulators, which is compared to our Model Sim Intel FPGA Starter Edition. So it is the greatest advantage that it also have support to system Verilog, and then it is very easy for us to perform assertion based verification and then do functional coverage with system Verilog. You can go through the review quick start guide here. And there is one more important question that you may get in your idea, whether the Questa Intel FPGA Start Edition software is the same as the Questa Siemens EDA Questa core software. If you say no, they are different because the Questa Intel FPGA Edition software only supports the Intel's Quartus simulations libraries, whereas the Questa core can support any simulation libraries. Okay, and you can see the documentation here, the Questa Intel FPGA Edition Quick Start Guide. You can get the documentation, and you can also get the user guides from here. That is for Pro Edition as well as for the Standard Edition. Similarly, if you move on to the download center for Intel FPGAs, in the earlier case, when we asked you to download the tool, we have installed the Model Sim Intel FPGA Starter Edition software. But now, if you expand this Intel Cortex Prime Design software, and we move on to the Intel Cortex Prime Lite Edition, and now you can see that Intel Cortex Prime Lite Edition Design Software version 21.1 for Windows. So if you click this version, you can see in the multiple download, right? You can see what are the informations that are available, and on the individual files, right? You can see that it includes the NIAS2 EDS, and you can also see Questa Intel FPGA edition that is available. Right, so this is available as a software, and you can get licenses for the Questa Intel FPGA Start edition, and then you can work on system Verilog, and then we can verify the designs. Okay, so you can go to our page where 21.1, where you can see. Right, so let us go to the details. So what is this Questa Intel FPGA Start edition? The greatest advantage is there is no line limitations. In the earlier case, we had line limitations in terms of Model Sim Intel FPGA Starter edition. We can have up to 10K lines. It is 40% performance on an average of Questa Intel FPGA Starter edition software. And you can also log into our self-service licensing center to get a free 1-year license. And you can renew that license in our self-servicing portal. And you can click on evaluation and free licenses tab. And the greatest advantages is a mixed language support. We use Verilog, System Verilog, VHDL, as well as System C. So I'll show you some important simulation things that could be possible with the Questa Intel FPGA Starter Edition, and what are the capabilities in terms of assertions and coverage analysis. I can show you with an example. And what is the main reason of moving into the Questa Intel FPGA Edition? So the main reason for this replacement is to improve the simulation performance and experience, because the Questa, right, the full edition has almost all the features of the Model Sim edition, but then what is the greatest advantage is like it is up to 5 times faster for Verilog and 2.5x faster for VHDL. And what is very important is it can support the system Verilog assertions, and UVM is not supported, but then still we can get support for the system Verilog assertions. So how the system Verilog assertions are supported, and how do we analyze the coverage with the Questa Intel FPGA Starter Edition? That is the one I'm going to show you demo. That is the special session on the simulation and debug. Let us get into it. The Questa GUI will exactly look like the way how you can see Model Sim, but then there are fundamental differences because there are other features which could be invoked with Questa GUI, and how those things could be enabled, and then what are the advantages of performing that specific scenario that we will discuss now. What are the known differences between the Questa Intel FPGA edition and the Model Sim Intel FPGA edition? Let us understand that now. When it is the Questa Intel FPGA edition, that requires a license, but you can get that license from our self-servicing licensing portal. Whereas the Model Sim Intel FPGA Starter edition does not require a license. And you can also get for user action for Questa Intel FPGA edition, which you can obtain the license at no cost from Intel. So this you can see that you can use this for Starter edition, and you can get the license, and then you can ensure that you can perform simulations in terms of system Verilog. Right. So with this, let us move on to the logic. Let us describe and understand, like we know about system Verilog, but I'll just need to give a quick recap of that in order to see some simulation developments. System Verilog is the first HDVL, which is the hardware description and verification language. So earlier we were using Verilog and VHDL. So the Verilog and VHDL are called design languages. And then we were using verification languages like Vera and Specman, etc. They are called as hardware verification languages. So we had HDL and HBL. Now System Verilog is the first HDVL, which is the hardware description and verification language, where we are dividing the language into two parts. The System Verilog extensions to Verilog can be generalized into two primary categories. One is the System Verilog for design, and the other one is System Verilog for verification. Now, System Verilog for design is one which is having the enhancements which are primarily addressing the needs for hardware modeling, both in terms of overall efficiency and abstraction levels. So the System Verilog for design enhancements will be exactly looking like the Verilog only. You can say it is an advanced Verilog because the System Verilog is the third generation of Verilog. The first generation of Verilog is Verilog 1995. The second generation of Verilog is Verilog 2001, and the third generation of Verilog is Verilog 2005, which is renamed as System Verilog. Now, when we say System Verilog for design, it is exactly looking like the features like where you can use it for design. So in most of the cases, you don't require Questa there. We can use the same model sim to perform simulation, and you can use the Quartus for performing synthesis and fitter operation. Whereas what is very important here is when we divide the language for verification. So when we take it for System Verilog for verification, what happens is we have verification enhancements and assertions for writing efficient race-free test benches for very large and complex designs. So the System Verilog for verification provides you the details where you can write assertions, and we can write race-free test benches, and then this is for large complex designs. That means the basic idea is like the primary focus is to write the model, the RTL model for larger designs, and then we should verify the same, right, for larger designs. That is the wider scope of System Verilog. Right, so let us get into the details of the verification, and then I will show you some important features in the slides, and then I will walk you through the demo using the Questa Intel FPGA Starter Edition. So what is an assertion first, and then since the System Verilog assertions are supported in the Questa Intel FPGA Starter Edition, let us understand the definition of assertion, and then we can see how the immediate assertion is taken into account and concurrent assertions are taken into account. So an assertion is statement where in which we need to ensure that what is the property that is specified that need to be respected. If the property that is specified in the assertion passes, then we say that it is respected. So that means the assertion gets passed. If the property that is specified in the assertion is not getting respected, then in that case, the assertion fails. That means an assertion specifies the behavior of the system. They are primarily used to validate the behavior of the system. So based on that, we divide them into two. One is called immediate assertion, and the other one is called as concurrent assertion. One is called immediate assertion, and the other one is called as concurrent assertion. Yeah, what are immediate assertions? When you say the immediate assertions follow simulation event semantics for their executions and are executed like a statement in a procedural flow. That means immediate assertions are primarily intended to be used with simulation. That means it is ideally used for combinational logic block where there is no clock event involved. Whereas when it is a concurrent assertions that is based on the clock semantics, that means we are going to assertions which describe the behavior that spans over time. Let us see that how these specific assertions are going to help us in terms of the Questa Intel FPGA edition. Let us see that. Let us go through the fundamental examples. Like you can see that there is an example related to a multiplexer. So there is a 2:1 mux example here where we write always underscore comp. That means in System Verilog, you don't want to write always Okay, you don't want to write any parameters in the sensitivity list. When I write here always underscore com, that means it is meant for combinational logic. So when the select line is X, then there is no point in getting into the simulation. That means you can see that assert, if select line is not equal to 1 tick Bx, then you can say that, okay, you continue the simulation. That means you can enter into the block. If there is a problem, that means if the select line is X, then you should specify that the select line is X and then you should provide an error. Now what happens is, if it is a normal traditional Verilog code, what happens is like you may not get this logic, because even the select line is X, it will automatically enter into the else statement and it will provide the value of A. So this may be the problem for us. Now when we do the same with the Questa, right, when I say force select 1 Bx, when I say and then say run, automatically you can see that select is equal to X and I'm able to see there is an error that could be fetched by the tool. So this support is available right now with the Questa Intel FPGA Starter Edition. And this is for a specific 2:1 mux example where it is a single bit. It is also possible sometimes to do with multiple data. For example, if the select line is 2-bit, if any one of the bit is X, then there is no point in proceeding further. You can say that, okay, there is an error. And you need to say that, okay, when any one of the bit is X, then you should say it is an error. This helps us to improve the observability. So what is the observability when you say that when you are getting the input as X, right, then there is no point in continuing the simulation. So there are different severity levels that are available. So that specific logic could be approached with the Questa, right, and that could be directly approached with System Verilog also. And this is the third example which I wanted to show you. In that case, there may be a question where why we are looking only on the select line. There are cases that if any one of the input is X, right, then there are chances that there is no point in continuing. If you see the code now, there are two inputs, in1 and in2. If any one of the input is X, then there is no point in continuing. You can say that the input is X and you can see that it is showing the error. So the greatest advantage is assertions are going to improve the observability of a design. That means they are going to improve the simulation. It is going to provide error or warning during simulation. And assertion statements are not synthesizable. That means they are not going to be synthesized and they are going to be ignored by the synthesizer too. So therefore, it is very easy for us to improve the observability and understand that in terms of the simulation during Questa. Right now, all these three examples are shown. And let me again walk you through one more example with respect to concurrent assertions before we enter into the coverage. Now, if you go through the counter example here, what are the two important things that need to be addressed here? You can see that if reset, then count is equal to 0, else count equal to count plus 1. That is exactly same like your normal traditional Verilog code. What is the change that has been assigned here? Assign t equal to and count is given. The meaning is whenever the counter counts from 0 to 14, then we say that the value of t should be 0. And whenever the counter reaches 15, then I should say that the t should be 1. So now we have the RTL code, we have the module, and we have specific assertion statement, which is called as an assertion property file that helps you to verify whether both properties are respected. So what is that property that need to be respected? When you say at every passage of clock, what we need to check is if it is reset, then there is no point in continuing. You can disable. If it is not reset, then we should check that the count is less than 15. Whenever the count is less than 15, then we should say that it is negation of t. That means it implies that in the same clock cycle, the value of t should be 0. At the same time, what we also check is whenever the count reaches 15, then the value of t should be 1. Now, this property will be very, very helpful for us, because what we can do here is, with the help of the Questa, we can check both properties. When the counter counts from 0000, right, to 1110, we should check whether the t is 0. And the counter becomes 1111, we have to check that the value of t is 1. Now, this is the assertion property file. And we have the RTL code as well as the assertion property file. Both can be brought into the test bench, which is the top level module. Now, what we are trying to do is, like, we bring the assertion code and we bring the DUT and we say dot star. When we say dot star, that means if the signals are not connected to the same net, then you don't want to write named associations like dot A is connected to A like that. We can write that as dot star. That means all the signals are connected to the same net. So clock is connected to clock only, reset is connected to reset only, count is connected to count only, T is connected to T only. Then we don't want to write it twice. So that means it can just say dot star. Right, this is a feature of system array. Right, now what we can do is, like, we wanted to bind that and see how Questa takes care of this. Okay, I will just show you a quick demo about that. Let me show the simulation. So there is a lab on that, lab 2. I will copy all the codes, whatever I showed you right now, and we take it to the C drive. And here we can create a folder and say Questa assert. Okay. Inside this, we can paste all the 3 files. Now we can come to the start and say Questa Intel FPGA Starter Edition. You can see that, which is the Questa Intel FPGA Starter Edition tool, that we can open it. So it exactly looks like your model sim tool. Now we can say in the C drive, you can see the Questa assert. So you can get into that, and we can open that. So file, and we can open all those files right now. So if you wanted to cross verify, we can verify those information here. You can see this is the RTL code, that is the counter code. We have the assertion file. Then we also have the top level module where we have binded. Okay. Now let us compile. So compile, it is exactly same like how did you compile the same logics here. Okay. Then we can simulate, start simulation, and then we expand it. And which is our top module is this bind assertion. So we can take that bind assertion and we can simulate that. Okay, now we can say, okay, now what we can do is, like, we can see how it works out on the simulation. Now, if you go through the output, right, whenever the counter counts, right, from 1 to 14, you can see that the t is 0. Whenever the counter becomes 15, you can see that the t becomes 1. So you can see that. So that exactly shows that how the assertions are getting passed. That information we could see here. All right. Now, what you can also see from this specific logic is, like, you can specify and check whether the assertion logic is also available here. Okay. Right. So these are the important informations that will be helpful for us, and you can also get into it and see what are the specific options that are available. That information also we can. So all the compilation options and then the simulation options that are exactly same like your model sim simulation. But then there is one more important characteristic which we are going to discuss, is called as the coverage. I will explain that in the next demo. Right. Now let us move on to the next one. There are different types of coverages that could be possible in verification. What is called statement or line coverage. That means first we should understand what is a code coverage. When you say it is a code coverage, it is going to explain to us like what is the efficiency of the test cases that is generated in the test bench, how well the test bench is written, or you can say that how the RTL is exercised by the test bench, you can say, right? So you can just see how many test cases we have passed in the test bench, which covers the entire RTL. So now in this specific scenario, there are different set of coverages. We say statement or line coverage, block or segment coverage, condition expression coverage or focused expression coverage, branch or decision coverage, toggle coverage, path or extended coverage or extended branch and FSM coverage, like that. I will just give one line about them. And then I will also tell which are supported by the Questa Intel FPGA Starter Edition. When we say statement or line coverage, that means that shows that how many lines are covered, right, by your RTL. Which lines are covered and which lines are not covered, we can take. Block or segment coverage means which blocks are covered and which blocks are not covered, you can say that. But the block or segment coverage is not directly available in Questa. So the condition or expression coverage, when you say that what are the conditional operators, like you have logical operators which are available in the language, like logical and, logical or, logical not, etc. So how those operators are used in the code, whether they are exercised for all the combinations or not. I'll just give you a simple hint. For example, you have say A and B, which is double AND, okay? That means in that case, I need to have all the four combinations like 0 and 0, 0 and 1, 1 and 0, and 1 and 1. But in my test case, if I'm writing only 0 and 0 and the remaining 3 test cases are not written, then I have covered only 25%. Branch or decision coverage, when you say the if-else statement, case statements, all those statements would be covered under the branch or decision coverage. Toggle coverage, when you say that, it shows that how many signals are toggled. That means how they toggled from transited from 0 to 1 as well as from 1 to 0. And the path or extended branch coverage is an extension of the branch coverage, which is still not available directly in the Questa. So the block or segment coverage, path or extended branch coverage is not available. But the other 5 coverages like statement or line coverage, condition coverage, branch or decision coverage, toggle coverage, and FSM coverage is available with the Questa. So FSM coverage means you can also see the state, which states are covered, and how many transitions are covered. What are the legal transitions? All those things we can see with the Questa. So I'll show you a demo of that. It will give you a clear picture of how that would be helpful, right? So let me walk you through a simple example here. So first, let me copy those codes, and then I will explain the code, and then I will do the steps one by one. I have created a folder called Assertion Coverage, and then inside that I have the code and the test bench. First, let me open that with Questa, and then we will try that. So simulate, you can say end simulation. Okay, so now you are in the C drive, so you can come out, and you can see that assertion underscore coverage. So let me open that file. So file open, and in the C drive, assertion coverage. Okay. Let me open both. If you go through the code, let me explain the code as well as let us understand that as well. Now you can see it is a simple arithmetic logic unit, an ALU example here, where we use the parameters for all the operations like add, subtract, increment, decrement. Then you have compare, and, or, XR, etc. As I mentioned earlier, we are going to use just write always underscore com. Therefore, we don't need to provide any sensitivity list parameters. But then what we are trying to check here is we write assert statement to cross verify if any one of the input is X, that means in the select line out of 3 bits, if any one of the bit is X, then we should say assert select equal to X. That means it should show you an error. And in the X and Y, which are the inputs, like which are 4-bit, if any one of the 4-bit data is like, if any one of the bit is X, then it should say that it is $here. And in the case statement, you can see there are multiple operations where you need to perform addition, subtraction, increment, decrement, then you need to perform complement, and or XOR. All these operations are provided here. Now, when we go through the test bench, what is important for us is like you can see that we need to randomize some of the values. I have given here $u random, which is an unsigned data. And I have also passed the inputs with X. What is the meaning is if any one of the input is X, definitely we have a problem. Right? So that is our major issue. We cannot directly say $u random when you say. When you say it is going to generate some data, and you can also see here we are just forcing some data which are having X. Therefore, that will affect our assertion. Okay. Now, what are the 2 important points that need to be noted down here? First, we are going to see the coverage of the assertions, and then we are also going to see the code coverage. What is very important for us is like the code coverage should also be 100%, and the assertion coverage should also be 100%. Are we covering that in this design or not? Let us explore it, and then we will identify what are the drawbacks and how do we rectify them through the kind of simulation what we have. Now, let us perform the compilation exactly the similar way. There is no change. It is same like model sim. You say compile, you compile the code. Right, done. Right. So, what are the things that need to be kept in mind before we perform the compilation here? So, why we did so just to see that are there any errors? Okay, there is no error. But then there are some settings that need to be done during the compile options before we invoke the coverage and check the logic in Vesta Intel FPGA starter edition. So what are the things that need to be addressed here? We should go to compile. And then you can see here compile options. We expand the compile options. We can see it shows VHDL, Verilog, and system Verilog. And then you can see the tab called coverage and then system C. I told that it also supports system C. But in our case, we are going to discuss in terms of assertions and coverage in terms of SV, right? So in the Verilog and system Verilog tab, just click here, Verilog and system Verilog. It shows default. Use Verilog 1995, use Verilog 2001, and then you can see down, use system Verilog. We are going to use system Verilog here. And on the coverage on the right-hand side, that is, you can see the 3rd tab. As I explained in the slide, you can see there are different set of coverages. I told you there are 7 types of code coverage, but then as I mentioned that we are going to have only 5 coverages that is supported here. So you can see here enable statement coverage. That means it is going to tell that which are the executable statements that are covered by your RTL, which statements are not covered, you can find out. Then branch coverage, which branches are covered and which branches are not covered. Then condition and expression coverage that we can give. And you can see there are 3 toggle coverages. One, it shows that toggle, which is enable 0 or 1 toggle coverage. Second one, enable 0, 1 Z toggle coverage, because sometimes you may need to go to the Z, which is the floating, and then we need to come back. In some cases, we don't want that at all, 0 and 1. So I just wanted to explain like enable 0, 1 toggle coverage. That means whether all the signals are toggled from 0 to 1 as well as from 1 to 0, that we can check. And then you can see in the other coverages, you can see enable finite state machine coverage is there that you can just check. What are the 5 coverages we have enabled right now? Enable statement coverage, enable branch coverage, enable condition coverage, enable expression coverage, enable 0, 1 toggle coverage, and enable finite state machine coverage. So after applying everything, so in the compile options, we should click here then we should say OK. So now we have modified the compilation options. Earlier it was with default. Now we have given that we wanted only system Verilog, and then we have enabled the statement coverage, branch or decision coverage, condition or expression coverage, toggle coverage, and then finite state machine coverage. But there is no logic of finite state machine here, even though you click it. Whether this is an FSM, if you say no, only when it is a finite state machine, there is a point in enabling the FSM coverage. But then you enabled everything. Let us see what is happening. Okay. Now, what we should do is like first we compile the design. So again, we can go back and compile it. Now we need to go to simulate, start simulation, and you perform the simulation here by expanding the work directory. This is also exactly the same step what you follow in the models. Right, now what we are supposed to do, right? We should go to the library and expand the work directory and click the test bench and say simulate with coverage. Okay. Say yes. So after you say simulate with coverage, you can see that all the statements are showing X. But now what we can say is we can run them. Now once you run them, you can see the ticks here. That clearly shows that, okay, all these statements are hit. And you can also see that in the design that these specific statements are not at all hit. Why they are not hit? When you say the test case, whatever we have written in the test bench does not cover those things. That means it does not feed all those inputs to the DU. The RTL is not exercised by those test cases. So what we should do, we should modify the test bench in such a way that those test cases should also be added so that we will get 100% coverage. Okay. And then there is a problem in the assertion also, because we have some X inputs into our code. Because of that, assertions are also getting failure. You can see that there are multiple warnings here. Time 50 nanoseconds, time 70 nanoseconds. You can see the assertions are getting failed. How do we see the detailed report in the Questa Intel FPGA Starter Edition right now? So you can go to the tools and you can go to the coverage report, and then you can go to the HTML report. So tools, coverage report, and then you click HTML, and here you can click all the coverages, whichever we wanted, and just say OK. Now this shows the Questa coverage report summary, where the assertions, there are two assertions that are available, none of them is hit. Both are failure because you have X in the test bench. And there are 9 branches into our code. Out of that, 5 are hit, 4 are not hit is there. You may have a question that we have only 8, right? There are 8 combinations starting from 000 to 111. Then why it is showing 9 when you say that includes the default case also? Even though you don't have the default case, the compiler assumes that, okay, there is a default. Out of that 9 case, your code, that means your test bench, has only 5 test cases. So those 4 misses are there, which you can see there was a X in the code. And there are 31 executable statements. Out of that, 27 are hit, remaining are not hit. And there are 42 signals that need to be transited from 0 to 1 and from 1 to 0. But you can see there are only 29 hit and remaining are not. So now what is the basic idea is, like, you can see the percentage that we don't have 100%. 52.92 here. So I wanted to improve this to 100 when you say. So there are 2-3 things that we need to take into account. Let us go through the observations one by one. And the objective is not to immediately get 100 right now. The objective is to get an idea why our code coverage is not 100%. Okay, that we have explored it. Okay, so I'll give you the important clue how you can do that. The first one is your test bench should not have any X inputs. If a test bench has an X input, what happens? If any one of the input is X, then automatically the assertion logic will be disrespected and then it is not getting hit at all. Okay, what are the other combinations you can improve when you say? we have to modify the test bench in such a way that all the test cases need to be passed, number one. And what is another important thing that need to be noted down here is like we don't want the default case when you say, then there is an option available in Vesta where we can ignore the default case. That I will show you. So I will just do some modifications and show you the results, but there is a good way and good practice that need to be followed to achieve this 100% coverage. Okay. So the question is, okay, why it is 100%? If I am not doing 100%, what will happen when you say? There are some test cases which are not passed by the test bench. Now, when you debug the code, what is the basic problem is like, okay, some test cases has not been exercised. Then when you pass the test case and then the code is not working, then it would be a problem for us, right? We cannot stop at 50% and tell the customer, okay, 4 test cases will work and 4 test cases I cannot guarantee like that. Okay, that will be definitely an issue for us. Okay, so let us close this report and let us see what are the other possible options here. I wanted to discuss about assertions. When you say yes, you can just open this assertions tab here. And it clearly shows that there are 2 assertions which are of immediate type. That means it is based on the pure combinational logic block. And the language is SVA, nothing to do with the language here. Just understand the principle. So you can see that it is failure count. Now you can see that 2 times the X has passed this particular specific signal, and 3 times it has been failed. On seeing this assertion failure, you can see that, okay, it is because of this failure, since it is enabled and because of this failure, you are not getting the assertion coverage 100%. Okay. Now, can I get a simple report when you say yes, that is possible? In the code coverage report itself, in the coverage report tab, along with the HTML, you also have a text. So if you say text, you can just open that in the notepad. That shows that how many branches are there, in that how many branches are hit and how many branches are misses that we can see, and we can enable them. And it also shows you a total assertion coverage, 0%, and how many assertions are there is. And we can also see total coverage by file. Like if you see the total coverage, it is only 70%. We couldn't achieve 100%, all put together. Right. So what we do is like, there is one simple thing which we can think in the design. In the code, these are the 4 options you have: add, subtract, increment, decrement. Do you have those options in the test bench when you say, since it is random, it is generating the same test cases again and again, and it is not generating the test cases which are required. One thing is like you can increase this. One clue is like you can say instead of repeat 4, you can say repeat 15, repeat 20. Another case is what, when you say you have to remove these X's from the test bench. And what is the third case is, it is better that to remove this repeat also and try to feed them one by one. You know that what test case need to be passed, but it may not be easy in all the designs, right? But in this design, it is definitely possible for us. We can feed those test cases one by one, and we can improve that. Okay, let me just remove these X's in all the places and see, is there any improvement there? It may not, because this $random may be an issue, right? Let us close, save this, and then we can end the simulation. And then let us try once again. So we can again go to compile, click compile options and cross verify when all the things are available. Click here, use system vanilla, go to coverage. One important change I do here. You can see there is an option called ignore case statement defaults. Okay. Earlier we didn't enable this. Now I will enable this. That means you don't need to worry about the default case in my code. Okay. So just say apply, then you say okay. Now let us compile the design. So you go to the simulate tab, start simulation, expand the work directory and run the simulation here. And go to the library and say simulate with the coverage. And after you achieve it, you can say run -. Okay, you can see, are there any assertion failure when you say that it is only while starting? After that, no. Even though it is failure one time, then you may not get 100%. That's the problem always. Okay, right. So because at the simulation time 0, the signals are having X. Assertion may not improve, but is there any other improvement? Let us see. So go to tools, go to the coverage, and expand the HTML coverages. Right now you can see that. What is the improvement we got when you say there is a small improvement here? 8 branches are. Why it is 8? Because earlier it was 9, because it included the default case also. Now what is the clue we have got? It's like it is always better that we can feed those values one by one, because still it is going to select only the first 4 test cases. Right, you can see that. Now one improvement we got is we have got one more statement got hit, but still there are 3 statements which we knew that what test case need to be passed. So we have to feed that test case. That means a select line instead of $random. We can say select is equal to 3 tick p 0 0 0. And we can provide that it should be 1 1 1 or 0 0, which cases you want. So you give 0 0 0 0 0 1 0 1 0. You feed it. Definitely what will happen, there would be an improvement. Right? So that specific logic can also be added. What we can also try is like you can try to add those principles also here. Then you can say select is equal to, right, and say 3 tick p 0 0 0. Then again you can say that, okay, I will add that. Like this, you can add. And by this, is there any other specific? 52 was there, then 56 is there. Now, is there any other improvement? We can filter. So continue with this and check the compile options. It's very log coverages, everything is fine. Apply, no change. Now let us continue the compilation. Now go to the coverage and open the HTML. So from 52 to 56, we have improved to 69. But then there is one small clue. It's like, see, here all branches are done, but assertions are not. Why it is not happening? Because you start with the $u random, and initially the value of the input are X, right? So you have to think something here that helps you to improve the assertion coverage. These are some of the features which are available. I just wanted to show it to you where you can improve that with the Untitled FPGA Start Edition, because in the Intel high-level synthesis compiler also we use the system Verilog DPI. Also in the acceleration AFU use the system Verilog DPI. Please download that if you want. You can also get the license and you can practice this kind of examples. Stop sharing. Are there any questions here? Okay, if there are no questions, over to Biplav. Again, we can sync up in the afternoon.
Thank you, Padmanabhan sir. So now, dear participants, you can take the lunch break and please join at 1:30 p.m. Today being the last day of this program, we are having validatory session from 5 p.m. You have to join with the same link which is shared for you for today's session. And also I'm sharing the link for feedback. All of you can fill the feedback form. Thank you, everyone.
Thank you, everyone. Let us meet by 1:30. Good afternoon, everyone. Shall I start, madam? Shall I start, Biplav?
Welcome to the post-lunch session. The session will be taken by Padmanabhan sir. So now I request Padmanabhan sir to kindly start with the session.
Thank you so much, madam. Good afternoon, everyone. Let me start with the high-speed I/O interfaces lab demo, and I will provide the details to you. Then followed by we can have the course summary. We start sharing my screen. Right. So let us start with this. What is the objective of this specific lab? Is we are going to discuss about the FPGA high-speed lab manual. Now we are going to understand about the transceiver design flow for the Cyclone 5 device. So let us understand the flow here one by one. I will walk you through the lab manual, and then we can also try to do that with the help of the lab files. What is the objective of this specific lab? Is we need to understand about transceiver design flow. That means we are going to build a transceiver channel, install the tutorial files, and we are going to open the project and review the design and create a Cyclone 5 transceiver native physical instance using IP catalog, because it has both transmitter as well as the receiver. And we create the transceiver physical reset controller using the IP catalog. And then we are going to review the connections between the IP cores and the pattern generator. Then we can simulate the design, we can review the pin assignments, and then we can also compile the design and check whether all the timing requirements are met. And finally, we can go through the summary. So this is the high-speed interfaces lab which we are going to see. There are 8 steps. Let us go through one by one. And then I will also show you the demo. We are going to install the tutorial files, and we should open the project and review the design. And we create the Cyclone 5 GX transceiver native physical instance into the IP catalog. Create the transceiver physical reset controller using IP catalog. So we are going to bring both, review the connections, and then we are going to simulate the design, review the pin assignments, and then we can compile the design. This is the block diagram. You can see that this is a simple design. It implements the loop back connection between the single transmitter and receiver channel from a Cyclone 5 GX transceiver native physical layer, which is PHY. So along with this transceiver, we also have a reset controller that is also instantiated to handle the reset flow for the transceiver. So finally, a data generator block provides an alignment pattern to train the link between the transceiver and receiver channels. And we are going to generate the payload data. You have a transceiver reset controller, you have a data generator, and then you have a Cyclone 5 native physical layer. So all these 3 things are available, and we are going to explore them right now. First, we are going to install the tutorial files, and you can copy that into the C drive. Let me go through the steps here. In the Day-6, you have the HSIO design files .zip file. You can just copy that document. In the C drive, we create a folder called high-speed interfaces. and you can paste the entire things inside that, and we can unzip this, and you can see that these are the files that are available that is present inside it. Now, if you go through this, you can see it uses the QPF file, which is the Quartus project file. And then you have an SDC file, which is the synopsis design constraints file. You have a tickle file, and also you have a do file. And then you can see the top file, which is the top.qsf file, top.v, and the top tb.v, where you have the test bench as well as you have the do file for simulation. All these files should be available in the high-speed design, which project we are going to see. We are going to open the project, and then we should open the specific PF file. Right inside the HSIO design files, you have this PF, which is the Quartus project file. Right. So when we are targeting it for the Cyclone 5 GX device, right, you have to see here it is a Cyclone 5 GX transceiver device. Right. So what are the things that are required? You require the Quartus Lite edition, and please ensure that you have the Cyclone 5 device support. And we should also have the Model Sim Intel FPGA starter edition. You can click this Cyclone 5 GX starter kit user manual, and we can go through that in detail now. Okay, let it open it. Go to the Quartus Prime Lite edition. Go to open project and go to C drive and say high speed interfaces. Right. So what I can do right now. Okay, inside this we keep it. Open project and say high speed design. Inside that you have a QPF file. Okay, so you can open this top file. Okay, so this, if you want, you can have it right now. I'll show that to you. Now you can see this is the file Cyclone 5, which is a GX kit. It is a Cyclone 5 transceiver example. So we are going to use the Cyclone 5 GX edition kit. Here, you have a transceiver serial data, you have a receiver serial data, and then you have TX trigger as well as you have the RX trigger. And we can see 7 down to 0, TX, which is transmitter parallel data, and receiver parallel data. Okay, and you can see that the transceiver is instantiated as well as the reset controller is instantiated. So we need to bring these IPs into the design and complete the process. Okay, so let us do that one by one. And what is the logic here is you can see always at passage of the transmitter or reset. During reset, it should be 0. Whereas when the system is up and running, you need to increment the count so that the data would be passed. So this is a simple logic which has been written, which is the custom logic. So this is helpful for us to feed the transceiver parallel interface with the valid data patterns. Okay, right, let us go through this process. Now we have installed these files and we opened the QPF file, which is the Quartus project file. Now we need to go to the IP catalog and we have to search for the Cyclone 5 transceiver native physical version. Okay, it can be version 17.1 or whatever, but whatever version is available right now, that we can try to take it. Okay, so it should be Cyclone 5 transceiver. Go to the IP catalog and you can say here Cyclone 5 transceiver and then native. You can see that. Cyclone 5 transceiver and then native physical layer. We can take that. And what we should name here should be the native underscore physical layer underscore 1G. So please name exactly what is given in the lab manual. Otherwise, the interface, like what is been instantiated, that would go wrong. What is it is instantiated is in this name. Just to follow the name. Okay, so what you can say, native physical layer underscore 1G, native underscore PHY underscore 1G. Let it be okay. So select that. Now, once we provide, okay, so it has to ensure that the IP configuration wizard will launch. So you should ensure that you instantiated the correct native physical layer for Cyclone 5. You should open this wizard, right? You can see that. Okay, so this is the transceiver native physical layer for the Intel Cyclone 5 FPGA IP. You can see that this is native physical 1G. What are the informations we should do here? It's like you should see the general tab, data path options, as well as the standard tab. All those things, let us go through that. So now general tab, it should show it is fastest, and then the message level for rule violations should be error. That is fine. And the data path options, you can see enable transmitter data path as well as the enable receiver data path. And you can also see the standard options that are provided, as well as on the PMA, as well as in the standard PCS side. Okay, let us go through that one by one. Please ensure that on the tabs, it should be 1250, right, Mbps, and ensure that it is correct. So the data rate should be 1250 Mbps. What is important is in the configuration wizard, it is organized into sections and tabs, and this structure will be used to configure the IP variation. And we have to see the general and data path options. Sections will be configured first. So change the IP default parameter values only when it is indicated. That means only it is specified, then change the values. Otherwise, let it be common. For example, in this case, it is standard 1x1. There is no change. Okay, number of data channels is 1, and you don't need to modify anything. What is specified in the lab manual, just go through that. Okay, in the data path options, check enable simplified data interface. That means here we have to say simplified data interface in the data path options. Okay, so here you can see that in the specific logic, right? So we can click into it. So here you can see the data path option. You have to just say enable simplified data interface. So you can enable them. And you can see all other parameters should remain the same. By selecting enable simplified data interface, all unused signals from the native physical layer will be grouped together, making it is easier for the module instantiation. Okay, now you can see that there is a change in the instantiation. Right, now once we do this, you can see that the enable specific options that need to be there. Now we need to go to the PMA tab. This is the configuration tab. All the parameters will remain in the default values in its general section, but in the TX PMA section, whereas we have to set reference clock frequency to 156.25 megahertz. Okay, that's the clock frequency which we wanted. Okay, so in the TX PMA, it is 156.25. In the RX also, we wanted to give 156.2. Let us go through that now. In the TX PLL, okay, you can enable this now. Here you can change this to reference clock frequency should be changed to 156.25. Please ensure that we modify it. It is available here itself. Okay, so the transmitter value is also 156.25 and the receiver is also changed to 156.25. Don't need to modify anything here, and then enable the receiver set lock data. Just lock the data. It is already set it now. What is set there, you need to ensure that we unlock it. This is set now, and continue the IP configuration by unchecking the enable. Okay, so now we can just uncheck it. Now that is also done. Now go back to the next process. Now we have the PCS tab. All other things you don't touch anything. Okay, so that is the basic scenario. Go to the standard PCS tab now. In the standard PCS tab, general options, in the phase compensation FIFO section, in the byte ordering section, byte serializer and deserialization section, and the match FIFO section, and all these things we are going to have only the default values. But we are going to just modify in only one place. Okay, the standard RX or PX interface bit values need to be modified. On the standard PCS tab, both values should be set to 10 and it should be 8B or 10B encoder and decoder. Okay, so let us check that. All other values are same only. But what we are trying to do is these values should be set to 8. Okay, so these values need to be set to 8. Change that. Okay, so you can modify this information right now. Here you can see that it should be changed so that it should be 8. Okay. So please ensure that the values are taken into account, and then it should be of low latency. Yes. Okay, now we need to enable them. Let us enable that also. Enable 8B as well as enable the decoder. Enable them right now. Okay, it has nothing to do with byte series logic. Now you can change this. Now you can see the values. So now we need to go to the word aligner. There you should modify the values. For the rate match FIFO. So these values are done right now. And if we ensure that the receiver and the transmitter both are in sync, all the other parameters should be similar. Here in the word aligner and in the bit slip. Okay, this place we have to modify some more information. Here, instead of bit slip, we should change the value to synchronous. Once we modify that, we need to add some more values because the value what we provided is 10, not 7. So we change that to 10. And here we need to provide the value. Okay, so you can see that the 17C is the value which we are going to force it right now. So followed by there would be 7 zeros followed by 170. That is the 10-bit. Right. So ensure that it is done, and also other parameters don't need to touch here. That is same only. Okay, so follow that. And once all these changes are done, you can click the finish button and you can exit the project. Okay, so now all the parameters are done. You will just say finish. Okay, once it shows generation successful, you can exit. This is for the first case. Okay, now second, we need to bring the reset control. Again, we should type in the IP catalog transceiver physical reset control. So just say yes, to be added. Now here you type again transceiver. You can see transceiver physical reset controller. Open that. And please ensure that what is the name that is given, same you give, because that has been instantiated in the same name. Reset underscore controller underscore 1G. Reset underscore controller underscore 1G. That's the name you have to put. Okay. Once it loads the Mega Wizard, there are two more options which we need to do here. So in the general options, set that to 50 megahertz by selecting the Arya 10 default settings. Okay. So now go to the general options. Instead of setting this, okay, you click that and change this to 50 megahertz. But change this to logic. So you can see that. Okay, once you double click and you change this to 50 megahertz, because this is the logic which has been taken. Now you can see the values. Okay. Right, it will take the default settings. Nothing to need to worry. Now just click finish without modifying anything, and then you can exit from here also. Now you will have the transceiver physical reset controller. Both are available. Now you can review the connections by clicking the top. Okay. In the logic, you can see double click the top module. You just say yes, and you can see that there are in the top module. You should have all these things instantiated. So reset controller is instantiated, as well as the native 1G is also there. So Cyclone 5 transceiver is also there, which is an high-speed interface right now. Okay, let us perform the process. Now, when you click it, you can see there is no problem in the analysis. Let's see, is there any issue in the analysis and elaboration? That means, have you followed the IP catalog correctly like that? Now it shows that the quartus prime analysis and elaboration is successful, and it shows that 0 errors, and then it shows 3 warnings. Let us go through the netlist viewers and go through the RTL. You can see there is a block diagram here, and when you expand that, this is the reset controller, and you can see here this is the native basically. Both are available, and you have the reset, this clock, receiver serial data, as well as the reference clock. All are available. Okay, let us perform the remaining tasks. If there are any problem, then we can check it. If you wanted to simulate the design, you can simulate that using the do file here. So Also, we can also check that simulation logic. It's same like model sim. Inside this directly, we can run the do file. Automatically, you can see the simulation setup. Okay, now let us directly go through the synthesized process. In the pin assignments, let us say click on tools and then you can click tickle scripts here. So all right. So now the idea is like we have to see, ensure that whether the script is ready. Okay. Which script we wanted is we have to run the specific script. When you click this, so there is a cyclone 5 GX receiver 1G pins.tcl. Okay, we wanted that default pin need to be run right now. So select that, and the moment it gets selected, say run. You can say it is getting executed. It is done. Once it is done, you can close it. Okay, so the moment it gets closed here, now go to assignments and directly go to pin planner. Now in the pin planner, you can see that the receiver clock, reset, receiver serial data, and then sys clock, and transmitter serial data, transmitter trigger, reference clock, all those information are available. All right, now what we can do is we can compile the design, and you can also see what is the XTC file that is available. Okay, so now you wanted to get that STC file, what is available? Yes, I can just show that to you. That will give you a good idea of what is present inside the design. So let us go to the C drive, high-speed design. Inside the HSIO design files, you can also select for the STC file, which are available right now. So that we can check. So this is our top.tv file, which provide you the details. But then what we wanted is the STC file. Double click and open the STC file. There are two clocks, create clock. One is 20, other one is 6.4. And we have two clocks for the design now. One is the sys clock, which is the system clock. Other one is the reference clock, which is 6.4 nanoseconds. So both clocks are available right now. Right, let us compile the design. So the pins are taken into account. If you don't want this tickle window to be opened, so you can just say utility windows and say tickle. And let us perform compilation. And we can also see the timing report once it is compiled. What and all the information that need to be noted down here is, you need to know how many number of high-speed interface that it is taken. So on the receiver side, you can see that. In the earlier cases, we have seen it has taken only ALMs, registers, virtual pins, memory, etc. But in this, we are going to see high-speed serial interface. In the high-speed serial interface, what are the information that are going to take on the transmitter side, as well as in the receiver side, we are going to see. So once it is compiled, we are going to see the timing report also. And then that includes a summary. I will show you that. Let us wait for a few more minutes to complete the compilation process. So you don't require any other extra specific information here. If you have the Quartus Lite edition, in which a Cyclone 5 devices are installed, that is more than sufficient. Okay, now what you can do is, you can see here, as per the lab manual, you can see total high-speed serial interface receiver, and then you can see all those things. Out of 6, 1 is used like that. This information you can see. Okay, now if you expand the filter operation here, and go to the resource section and explain the resource usage summary, here we can see the high-speed informations. So here, standard TXPCs, channel PLLs, everything we can see. All the high-speed devices you can see here. And what are used by your design that we have seen. Okay, all right. Now, what are the other informations that we can also go through is the schematic after synthesis and implementation. So go to the netlist viewers and then go to the technology map viewer. So you can see that. Expand the tools, go to the netlist viewers and then post fitting. You can also check is there anything related to the state machine viewer in the netlist viewer. There is no state machine in this design, so it is empty. It is not showing anything. But we can check the chip planner. Okay, so this is the layout. And this is the IP which you used. Right, so hence the lab demo and the lab files are available. Okay, you can just synthesize and implement it. If you wanted to simulate it step by step, the steps are provided that you can try it on your own. But what I wanted is you have to check whether you are able to integrate the intellectual property into the design, and if you could compile it successfully and generate the reports, that would be great. Okay, so I will share this with you. So this specific information is available in the lab manual. Okay, so what I will do, I will share the HSIO design files.zip and the high-speed interfaces lab manual now in the Google Drive. And also what I will do, I will also share the session slides, like the PDF slides, what is discussed in the morning. I will put all the three right now. Then after some time, when you are working on the hands-on demo, I will provide the summary of the FTP. What we have covered in these 6 days and what are the key takeaways. I will explain that. So I will stop sharing. And I will share the details in the Google Drive. Okay. Just give me a few minutes. I will share the lab manual, the lab files, as well as the session slides of the FPGA acceleration. All the three, I will share that in the Google Drive. You can start working on the lab. Meanwhile, once you are working, I will also explain about the course summary, what we have learned in these 6 days. I'll provide an overview. I have shared the files in the drive. Please start working on the HSIO lab. Please follow steps. You don't need to concentrate on simulation right now since we have done many simulations earlier. What I want is just integrate the IP, perform pin assignments, complete the compilation, and then also check the timing report. Okay, I will also show the timing report right now. So let me share the screen. What we have seen is we have discussed about the filter operation. Let us directly go to the timing analyzer and create the timing netlist. And what we can do is we can take the clocks now. Click here, report clocks. Now you can see what are the clocks that are generated. From these clocks, you have the reference clock, which is 6.4, and sys clock is 20 nanoseconds. Here 6.4 is the one which we have set. You can remember that. 156.25. And the system clock we set that as 50 megahertz. That's for Arya 10 devices. And just select that library and then we modify it. You can remember both, right? Now what we can also check is the timing. Report timing. And for the setup, right? Let's see. For one clock domain. So from the reset controller to the sys clock, right? You can see from the launch clock to the latch clock, you can see the slack is a positive number, 1. So the data required time is 27.016 and the data arrival time is 26.016. So you can see slack is 1 nanosecond. So it is positive. So if you see here, this is the launch clock and this is the latch clock. And you could see the slack is positive. And also we can check for hold, report timing, and check hold here and say report time. And even for hold analysis, it is arrival time minus required time. It is again a positive. And the third important information which we can also check is the report clock interaction, whether that works out or not. We will see. Is there any? What is the interaction? Let us see. The histogram. So you can give one clock here. This clock. So you can see this is the address, and this is the slack. Now you can also check this report with respect to another clock. This is for the reference clock. Right, so there is nothing available. So because that is for the system. So what are the information that we can see? Are there any exceptions available here? You can see that report exceptions. Now you can see set false path available in the constraint, and there are set max delay that is available in the constraint. All these things are exceptions. As we know from our high timing analysis session, what are timing exceptions? If we say we know about the pure combinational logic paths, as well as the false paths and then multi-cycle paths. But in this case, there is no multi-cycle path. While performing the lab, we did about the multi-cycle path. But here in this case, there is a set max delay. And then we also have a set false path. So when it is a set false path, then the paths won't be analyzed. The informations are available here. I request you to go through the entire step because you can complete this lab without performing simulation. If you think you can complete this within 45 minutes. You can start working on the intellectual property, then you can perform synthesis, implementation, and then you can analyze the time. Right, so just follow the steps. Meanwhile, I will share the acceleration slides PDF in the drive. And please let me know if you have any questions. I've shared the PDF version of the FPGA acceleration slides in the drive. You can have a look at it. And you can also try the HSIO lab, what is given to you. I have shared the lab manual as well as the design files. You can start trying it. And then meanwhile, I will also share you about the Cyclone 5 GX starter kit. We have downloaded it. I will just open that and show to you. This is a Cyclone 5 GX starter kit user manual, where you can see it has the control panel using the starter kit, and you have multiple examples. So these examples are based on the system builder and RTL based example codes. One is on the SRAM RTL test, and then LPDDR to SDRAM RTL test, and NIAS to soft core based examples are available. All these examples are required for you to understand about the Cyclone 5 GX. So you can download this device. This is the device which we have targeted for today's lab. And it has 18 LEDs and 10 slide switches. Okay, so it is not like our D1 SoC. You can see that. And you don't have a 6 hexadecimal display, you have only 4 hexadecimal displays. I'll stop sharing, and you can start working on the lab. And you can just put your queries in the chat and we can have discussion. Welcome back, everyone. We are going to discuss about the course summary. I've taken some files from each day's session, and then I'm going to just give an overview of what we have learned in this 6 days faculty development program. So let us start with what we have covered in each and every day, and what are the key objectives, and what are the key session topics, and what are the different hands-on labs we have performed. I will explain them one by one. So we started with day 1 with introduction to Intel FPGA, what is tool flow, and remote console lab. So let us understand the architecture. We started with the lookup table, which is the foundation. So the diagram shows that it is a 4-input lookup table, which is designed by using 2 3-input lookup tables and a 2:1 multiplexer. So now that is the basic component which is present inside the FPGA. Then we discussed about the adaptive logic module, which is called as an ALM. When we go through the adaptive logic module, which is an ALM, which has an 8-input lookup table, 2 3-input adders, and then 2 registers. So, which means it has an 8-input lookup table, right, which could be configured for power 8 different set of combinations. And 10 such ALMs are combined together in order to form a logic array block, which is called as an LAB. So 10 such ALMs are clubbed together in order to form a logic array block. And using the logic array block, if we build a memory, then we call that as a memory logic array block, which is called as an MLAB. That's what we discussed. So that is the first resource that is available. So we need to know about lookup table. We need to know about the adaptive logic module. And we also need to understand about the logic array block. Then we have a memory block, which is called as an on-chip RAM, which is an on-chip memory block. In the on-chip memory block, there are multiple ways we learned this. One, we have developed the vanilla code of the memory. Second one, we inserted that in the template. The third one, we can instantiate the memory in the IP catalog. So there are different ways. So what is available in the on-chip memory block? It could be configured as a RAM, or it could be configured as a ROM. As I mentioned earlier, it can work as a single port RAM, dual port RAM, single port ROM, dual port ROM, and RAM based shift register, as well as FIFO. These are the 6 configurations. You can use the block RAM, which is the on-chip memory that is available inside the Intel FPGAs. Then we discussed about DSP blocks, which are called as a digital signal processing blocks, which can work as a dedicated multiplier. Right, so that was the logic which we discussed on the Intel FPGAs. Now this will give you an overview where when all these blocks, then we can interconnect them together. Sorry. Once we interconnect, we can see this is the Intel FPGA portfolio, where we can see the application specific performance, where we can see Intel Max 10, Cyclone devices, Arya, Stratix 10, and Agilex devices. This is our mid-range FPGA, and this is our low-cost and low-end FPGAs, and Stratix 10 and Agilex, which are our high-end FPGAs. This is what we discussed during our first day. And then we entered into the Quartus tool flow. To give a simple recap about the Quartus tool flow, we discussed about the Intel Quartus Prime Design software full compilation flow, where we started with RTL. We performed analysis and elaboration, and we performed a functional simulation. When it is analysis and elaboration, we need to check the syntax, and we should check the semantics, and it performs initial synthesis. And we perform the functional simulation to verify whether the design is functionally correct. Then we performed pin constraints we applied pin constraints, we performed synthesis and filter operation, we generated the programmer file, and then we implemented the design onto the FPGA. When we do that, we discussed about the remote console, which is called as the LabsLAN setup. Then we discussed on the timing analysis on the second day. The first day focus was on making the design, perform functional simulation, perform analysis and elaboration, and we apply pin constraints, perform synthesis and filter, generate the programming file. The next thing is we have to understand what happens during the synthesis process and what happens during the filter process. I'll just give you a recap. When it is synthesis, it translates the HDL source files into an atom netlist so that the code would be converted in terms of logic cells, flip-flops, IOs, RAMs, DSPs, etc. And when we are performing filter operation, as I mentioned earlier, there are 4 stages in the filter. And each and every stage, we call that as a checkpoint, which is called as CP. It is also called as a snapshot. Right. So now what is very important is why do you want to do this step by step? That may be the question when you say. There are chances where your placement and routing will take more time. It will be time consuming than any other steps. When the design is taking 8 to 10 hours of placement and routing, and finally if the design is not meeting timing, then again we need to identify what is the problem and then you should start debugging the design. So instead of that, what we can do is we can do step by step where before performing the routing step, we can check whether after the placement, whether the design is meeting timing or not. If it doesn't mean, there is no point in continuing further, we can go back and then check what is the problem. That's what we have done here. And then we call this as snapshot, and it is also called as checkpoint. Right. Now, on the first day, we did 2 traditional flows. One is directly we implemented the design onto the board, which is physical. The second, we also tried with the LabsLAN. The advantage of LabsLAN is the virtual labs with the remote console, where we can have a local system where we could perform synthesis, filter, generate the SRAM object file, and we can upload our SOF file to the LabsLAN setup. That's what we did. And to recollect, you have created one login, and they are real laboratories and they are not just simulations. There are 2 modes that are available in the LabsLAN setup. So what we discussed is we used the no IDE mode. In the no IDE mode, what is the advantage is we have the installation of the tools in our local system. And after generating the SRAM object file, we'll directly upload that SOF file in their LabsLAN setting. This ends the day 1. That was the logic we discussed. Then day 2 on a Sunday, which is 13th March, we started with timing analysis and timing closure. So there are 3 important points that need to be addressed on the day 2 contents. We need to understand about the timing analyzer. So before getting into the timing analyzer, we got into the details of concept of timing analysis. Different set of timing analysis, like different types, like what is standard timing analysis, what is dynamic timing analysis, what are start points, what are the end points, what is a setup violation, hold violation, clock arrival time, data arrival time, setup slack, hold slack, so many things we discussed. After going through the paper and pencil exercises, we started with the timing analyzer in the Quartus Prime design software. And the flow is simply captured here. To recollect, you can see that we start with the synthesized design. We need to apply the timing requirements. Then you can configure that in the timing analyzer. Once we do that, we can again perform filter operation, and then we can verify the timing in the timing analyzer. So there are 2 more slides. That is the third one. The first one is the timing analyzer. Second one is the flow, what we did. The third one, what are the steps or what are the key takeaways? How do we fix setup violations and how do we fix hold violations? That was our discussion. As you can recollect, you have to ensure that the design should not have any setup or hold violations. So to fix up the setup violations, a setup violation occurs when the data arrives too late compared to the destination register's clock speed. We can tell fitter to try harder or confine logic to a smaller area, and we can rewrite the code to remove logic stages, and then we can add pipelining, and you can slow down the clock, which is undesirable. So as we discussed in the paper and pencil work, okay, we can do slow down the clock. We, instead of 20 nanoseconds, we can increase it to 21 like that. But that is not the case when we do that with real time. So therefore, there are multiple techniques that could be adopted in order to fix the setup violations. Similarly, when we wanted to do hold violations, in that case, the data is very fast. We need to insert buffers in the data. So the greatest advantage is Qualtus will automatically attempt to fix those parts by adding delays. But what we need to also check is, if you go on adding delays in the data path, it should not affect the setup time. It means you should not get a setup violation. So this was the key takeaway. And then we had lab demos on this, and then we had hands-on with the timing analysis. And finally, we discussed on the clock domain processing also. Okay, so that was our second day. Then third day, we went into the high-level synthesis. Okay, so the timing analyzer, and then we moved on to the HLS. That is our third day. So we discussed about why HLS. That means the first 2 days we were developing the RTL code, and we converted that into the synthesized netlist, and then we performed fitter operation, generated the programming file, and we checked the timing, everything. The third day, we wanted to convert the C or C++ code, the high-level code, into an RTL. That was our objective. So just a recap, Verilog or VHDL code are hardware description languages. They are not algorithmic in nature. What we wanted to do is we should use C++ instead of RTL as a primary design entry language. So therefore, what we can do is, like, the C++ level execution enables verification that is orders of magnitude faster than the RTL. That's what we do that. And what happens inside the Intel HLS compiler is, you give the C or C++ code into the Intel HLS compiler, convert that into a Verilog code, and then take that to the Intel Quartus Prime design software and implement the design onto the Intel FPGAs. What are the benefits? When you say you have ease of use, it is FPGA quality of results and partnership and ecosystem, because we can use the GCC compiler, and that could be downloaded, and that could be integrated into the Quartus Prime design software, and we can combine the results. The FPGA quality of results, that means the HLS compiler is going to provide you the results in terms of adaptive logic modules, DSP resources, memory resources, etc. And we also had some case studies on when do we need to go for high-level synthesis and when do we need to go for RTL, like that. We compared on the RTL versus HLS. And we came up with some conclusions stating that RTL-based method would be best for the precise timing, where we have state machine and control-centric operations, because it is very easier to control the number of resources used and aligning the edges related to the clock cycles. Whereas when we use high-level design, it enables productivity gains for problems that involve vector arithmetic. It is useful and good for video, AI, compression applications, etc. Even though it is not as optimal for area and performance, but then it is quicker development. But you can also see that in the case study, we have seen that it is having good performance. We can achieve better performance equal to our hand-coded RT. High-level design is excellent for algorithmic development and analysis, very quick to simulate, and it is easier to create test benches. And development iteration cycle improves by 3 to 5 times. So this was the logic. And then on the third day, we had demo related to the high-level synthesis. In the afternoon, we did HLS high-level synthesis of a 32-bit square root component, right? So that is the specific scenario. And you also had the multiple choice questions at the end. And in the afternoon, we discussed about the platform designer, and then I introduced you about the NIAS2 soft core processor and the NIAS2 soft core processor based hardware design that we did, and understood that how do you connect the components in the platform designer, which is a system integration tool. So we understood about the intellectual property, what is an IP, and we integrated the IP, and then we also seen how to create a memory initialization file, integrate the memory components into the design, and create an embedded system using the NIAS2 processor. That means embedded system design using the NIAS2 processor, the hardware design. And then we generated the HDL from the platform designer, integrated that to the Qualtus Prime design software. Right. On day 4, we started with the AI concepts, Intel FPGAs for AI, and then we had special sessions on simulation and debug. To give a simple recap, we started with definitions of AI, machine learning, and deep learning, what Raghavendra Bhatt has introduced. We have seen that artificial intelligence, which is the human intelligence exhibited by machines, and the machine learning is an approach to achieve artificial intelligence, and the deep learning is a technique for implementing machine learning. So after we discussed about the conceptual understanding of the AI, we moved on to why do we need to use Intel FPGAs for machine learning. That was the discussion. So what is very important is, you can see on the left hand side, you have M20K memory. And what we wanted is, we wanted multiplier and accumulate unit. That means you need to handle the floating point DSP blocks, which are configurable distributed. Why do we need to use Intel FPGAs for machine learning? Because the convolutional neural network, CNN, are compute intensive. We wanted to use, they are parallel in nature. You have a tightly coupled high bandwidth memory. You have programmable data path. They are highly configurable. And we got introduced to Intel Stratix 10 NX FPGA. So in the Intel Stratix 10 NX FPGA, the DSP blocks are replaced by the tensor blocks, which is called as the AI tensor blocks. And then we discussed about the signal tap logic analyzer, how to debug that in the afternoon. And we got an idea how we can use the signal tap debugging. Right? What are the pros and cons? We took a memory design where that memory had the DPRAM, which is a dual port memory. It had a memory initialization file. We simulated the design, synthesized the design, implemented the design onto the board, and then we used the signal tap logic analyzer to check what is the value present in the dual port memory. This was the day 4, and day 5. We started with the embedded system design using the Intel SoC FPGAs. We started with what is an Intel SoC FPGA? An SoC FPGA is one which has the ARM, which is the dual core ARM Cortex A9 plus FPGA. So ARM plus FPGA is equal to SoC FPGA. We discussed about that. And we also discussed about the ARM processor system, which provides the best of both worlds. And we had multiple labs and then hands-on with respect to how do we create a system. In that case, we used the Cyclone 5 device. To give a recap, we have gone through the low-end SoCs and then mid-range as well as the high-end SoCs. I showed you some slides which has Cyclone 5 and Stratix 10 in the session slides to compare with the low-end SoC with the high-end SoC. Because this has a dual core ARM Cortex A9, whereas it has a 64-bit quad application processor A53. You can recollect this typical design flow. before entering into the debugging, first we took a design and then we configured the design in the platform designer. We instantiated that in the Quartus Prime design software. We performed analysis and elaboration, synthesized the design, implemented it, and then we took that to the debugging software where we used the system console as well as the signal tap logic analyzer and verified the SOC FPGAs. Also, we discussed about the NIAS2 processor-based embedded system design where we use the software build tools SBT. We discussed about both the hardware as well as the software design. And we had 3 lab demos and hands-on sessions, which I have also shared with you to practice it. And we have to start with the golden system reference design, which is called as the golden hardware reference designs, which are available from the Terasic website as well as it is available in the rocketboards.org. We have also taken the reference design from our Intel design store, dev store for Intel FPGAs, and then we have gone through the projects related to Cyclone 5 device. Now, we have also gone through the debugging design, where if you have a complete system and you wanted to debug, then it is very, very tough task for us. So in order to debug that, we use the debugging mechanisms, which is the system console and the signal tap logic analysis. A simple recap of the system console GUI. And today we discussed about the FPGA acceleration in the morning, which is the portfolio of the programmable acceleration cards, which is Intel Arya 10 and then Intel Stratix 10. Okay, I will just show you where you can get more details from our website. So you can just say Intel Arya 10 programmable acceleration card. You can just say Intel Arya 10 pack. This will take you to the page where you can get more details about our Intel programmable acceleration card with Intel Arya 10 GX FPGA. You will get more details about this, about that. So I can just paste that. You can get more details here. And you can also get more information related to the kind of trainings what you can get with the Arya 10 GX. And you can also try that with Intel Stratix 10. Programmable acceleration card. So this is the Intel FPGA pack, D5005. So this is based on the Stratix 10. So I will share this information also with you. You can try that also. All right. So after that, what we discussed is we discussed on the Questa Intel FPGA Start Edition. We showed the demo on System Vanilla coverages, and then in the afternoon we have seen about the high-speed interfaces. I hope you would not have forgotten that. And these are the references and documentation which you can look into it. So this is the page which I showed you, Intel Programmable Acceleration Card with Arya 10 GX. That you can have different RTL development trainings which you can get into it. Like as Nilesh mentioned, we can go through this Intel, that is 01.org, where you have multiple informations. I will stop sharing, and if you have any questions, let me know. Thank you very much for your patience and then listening to us. Please try to complete the labs, and if you have any queries, please let me know. I will be available in the chat. So there was a question on the custom IP and the NIAS, right? Give you one small hint, okay? Let me explain that to you. You can get into the details more on the NIAS 2 handbook, okay? Let me start with this. For example, you create a new project wizard and say next, okay? And I say here custom, okay, IP and say peripheral, something like that. And then say top, say next, create it. You go to tools and then you open the platform designer. Here you can click a new component. Okay, and then you can name this new component. For example, it is my adder. And then I provide this name component, okay, display name, whatever you wanted. And then you wanted to see the block symbol. It will be showing like this. Then you have to click the files. Okay, here you should provide what are the files. Like you can say add file, and you have to add your Verilog file, whichever is like, for example, I have something like this. Okay, ALU something, you add this file. Right. So if you have a simulation file that you have to add. After adding this file, okay, so the moment, how do you wanted to add it for simulation? How do you wanted to add it for synthesis? Like that, we can add it appropriately. And then it is very essential that after adding these files, you have to add the parameters. Okay, and then you have to provide the signals and interface. What is the input that you have to say? That could be added as a custom IP. So this could be the basic idea of adding your custom IP, and that could be taken. So once it is there, you can add that also to your system contents. Okay, so please refer to that. You will be getting more idea how to bring your custom IP into the peripheral, and that also you can try through it. Okay, there are multiple reference projects available in the Intel Dev Store for Intel FPGAs. Select for NIAS 2 and select for Cyclone 5. So that will give you a good idea. So that you can get your project, so that it will become your component, and you can add that component there. Okay, so one more important thing. So let me close this and then try to show you one more, which already has a project, so that you will get some idea. I have an SOC lab. So let us open the QPF file. This is your top file. Now here, if you open the platform design, now you can see SOC system.qsys. Then if you click this register bank, right? So this is our Gorilla code. Okay, so this is our custom IP. So you can see register bank. So this would be taken as the model. You can see that clock reset. Along with your other interfaces, we can add this register bank also that is connected to this. Just the clock reset and then HPS FPGA interface is also connected. And this is our code. Okay, so this is a golden hardware reference design example, which is available in the Terrasic website. Okay, where you can find these kind of examples. I will show you. You can also go through that. That will give a good idea. Go to the D1 SOC CD-ROM, where you can go and find out demonstrations. We have seen SOC FPGA, the first example, my first HPS FPGA. You can go here, D1 SOC GHRD. And also you have examples related to HPS LED hex. This is on the hardware side, this is on the software side. And you also have some more examples related to HPS. So here you have around 4. And on the SOC side, we have around 4. And we have FPGA side around 10. You will get around 18 to 20 projects which you can practice on the SOC side itself. Okay. So please let me know if there are any other questions. Okay. Hello everyone, I have shared all the files as well as the presentation PDF slides, lab manuals, lab exercises, everything in the drive. You can have a look at it. And you can also practice the high-speed IO lab. So there was a question on the power analysis. That is definitely possible with the Cortex Prime Design software. What we can do is like you can go to the processing and then you can see there is a tool called Power Analyzer tool. So like what we have seen for timing, we can also take here Power Analyzer tool. When you click the Power Analyzer tool, it will ask you to start. That means you can see that what are the files you wanted to provide, or you wanted to just see the basic data, that you can click here. And it will run 100%. Now you can see what is the power data here. So we can see area here, the resources that are used, and then we can also see the timing analysis, the timing analyzer, and also you can see the power here. This is the power analyzer too. So once it completes 100%, we can see what is the power. You can see what is the kind of total power it has taken, that you can see. It shows 618.88 milliwatts like that. Okay, so you can start with any design because it's just an SOC design I've opened, but you can try with any design. So just the places like processing, you can go to power analyzer too. So there was a question in the chat related to the PDF help, okay, related to the quarters. Okay, it is available definitely. You can see here in the help tab, you can see there is a PDF tutorial where you can see that this is PDF tutorials for VHDL users, and then it is a PhD, that is PDF tutorial for Verilog users. Okay, just click the PDF tutorial for Verilog users. You can see that this is for Quartus Prime 18.0, and you can see that this is the version, and you can go through the examples here. What happens in each and every step is explained: design, entry, synthesis, functional simulation, fitting, timing analysis. So you can go through the steps one by one. Okay, this is targeted for multiple boards, like whichever board you have, you can go through the pin configurations according to that. Okay, let us take a simple example here. They use a light controller circuit which uses simple gates. The Verilog code is available here, and you create the Verilog HCL file and write a small test bench and perform functional simulation and compile the circuit. Okay, and then you debug errors. All these pin assignments are explained. So you have to refer to the corresponding pin assignments related to the boards here. So we have discussed on DE10 Lite as well as on the DE10 Nano as well as on the DE1 SoC. We can go through that. So implementing the design onto the board, JTAG programming, and you can continue testing the output. So till here it is there. So directly go to help, go to PDF tutorials. So this is the place where you get PDF tutorials. And wanted to see the version, I have already explained, but still if you wanted to see, you can see here about Quartus Prime. If you click here, this will show what is the version you use. Quartus Prime version 18.1. There was a question in the chat related to the platform designer. Okay, so there is a specific guide available there. So you can just search for introduction to platform designer related to the Quartus Prime design software, or you can also say platform designer Pro Edition or Standard Edition user guide. You have multiple videos starting from how to create a platform designer in the Intel Quartus Prime design software, create a system design with the platform designer, advanced system design using the platform designer. There are multiple videos that are available. And also you can see the user guide here. It shows the Intel Quartus Prime Pro Edition user guide platform design. Okay, so you can download the PDF here on the right hand side. Whichever version you want, you can click here. For example, whichever versions you want, you can select here and you can say download. Once it is downloaded, you can get the details of the platform design. Okay, there is a NIAS2 handbook as well as you have the platform designer user guide here. So here, adding the IP components into the system. This is one specific topic which you can go through, like how to add the components one by one. And you can add the parameters and how to select the parameters. All the informations are provided here. This is a very good and useful guide which you can go through it. You can get step by step how to add each and every IP component and how do you take the implementation time. For example, you have the Verilog code and you wanted to convert that as an IP. Okay, and then you can open the instantiation and add the files and then you create the IP variant. And you can connect the system components one by one and you can generate the design. So all these informations are available. It's an exhaustive guide, but wherever it is required, you can refer into it. I hope this answers the question. You can refer into Intel Quartus Prime Pro Edition or Standard Edition user guide, platform design. Right. So there is a feature difference between standard, light. Right. The standard and light will have the similar features, but then there is a difference in the Pro Edition. And there are multiple places where you can get the user guide. For example, I will share the link. Okay, so this is our Intel link where you can see that Intel Quartus Prime Pro and the standard design software user guides. So here you can see getting started, which is the Pro and standard, platform designer, Pro and standard, design recommendations, Pro and standard, compiler, Pro and standard, design optimization, again Pro and standard, programmer, Pro and standard, Block-based design is available only in Pro Edition. Partial reconfiguration in Pro and Standard. Third-party simulations, like whether we use the ALDEC or Cadence or Mentor Graphics or Synopsys VCS like that. Third-party simulation tools support in Pro and Standard. Third-party synthesizer tools like Mentor Graphics and then Synopsys synthesizer tools like Design Compiler DC. Debug tools that is available where we use the system console, signal tap logic analyzer, transceiver toolkit, in-system memory content editor, in-system sources and probes editor, timing analyzer, power analysis, design constraints, PCB design tools, scripting, so many things are there. Whichever guide you wanted, you have to just click here, standard or pro or whatever, and you can get the details of this. You can get the specific details, like whichever you wanted, you can just click. For example, you wanted to click the getting started for the standard edition. You can click that. That will take you to the corresponding page. So Intel Cortex Prime Standard Edition user guide. So here you can start. Is from starting the project, one by one, you can get into the details here. So on the left-hand side, you can see the topics like chapter by chapter, where you can directly migrate into sometimes also. For example, if you wanted to migrate from standard edition to the pro edition, you wanted to directly enter into that particular chapter, you can do that. Migrating to the Intel Cortex Prime Pro edition. You have a design that is available in standard edition, and how do you migrate that to the pro edition? So many things are there, please refer into that. So that will give you a good idea of getting more resources, right? Because the 15, 16 resources are required in order to complete the entire FPGA and SoC design. So there was a question on the FPGA boards for the Intel FPGA academic program. So you can search here FPGA boards for the Intel academic program. If you enter into the FPGA boards for the Intel FPGA academic program, here we have three major categories. So one is called as the teaching and project boards, and the other one is the embedded and robotic boards, and the third one is called as the research. These are the three categories where you can refer the Intel FPGA boards for the Intel FPGA academic program. If you see that teaching and project boards, you have DE1 SoC, DE10 standard, and then DE10 Lite. So in our workshop, we discussed on DE10 Lite and the DE1 SoC. The DE10 Lite board is the one which we use for all digital logic design applications, like whatever we have seen right now, right? You can see it has a NIAS2 processor, right? And then we use 6-7 segment displays and then 10 switches, LEDs, those things we use. And you wanted more details about this board, you can get details from here. User manual is here. Data sheets are available here. Quarters setting file with pin assignments is available, and synopsis design constraints is also there, where you have the timing information. And similarly, the DE1 SoC, which we discussed on the system on chip design session, right? SoC session. You have NIAS2 processor as well as dual core ARM Cortex here. You can create an embedded system design using NIAS. You can also create an embedded system design using the ARM. Both we discussed. And when you expand embedded and robotic board, we have DE10 Nano. This is what I explained to you yesterday, where you can have DE10 Nano, which is useful for IoT applications. And then you can also do from edge to cloud, where we use the Microsoft Azure. And you wanted to get more details about this board, you can get the user manual here, data sheets, everything here. And then the last one is called as the research boards. If you expand it, you can see DE10 Pro. This is based on the Stratix 10 FPGA, and DE5A Net DDR4 is based on the Arya 10. So this is Intel Stratix 10 GX, and this is based on the Intel Arya 10 GX FPGA. This Intel Stratix 10 GX FPGA has the ARM Cortex A53 quad-core processor, and also you have the soft-core processor, whereas the Arya, right, which is the Intel Arya 10 GX FPGA, has only the NIAS. It is not an SoC device. So yeah, so this you have basic details, but then you have multiple boards. But these boards are very helpful for performing projects and then doing embedded system applications and all those things. You can just refer into it. I hope that answered the question. Hello everyone. Again, there was a question in the chat related to the FPGA cloud connectivity kit and as well as the self-balancing robot. I have shown that earlier, but still go through the Terasic website where you can get multiple mini projects on SoC design. Here you have to select the SoC platform. Once you select the SoC platform, we will have FPGA cloud connectivity kit. So this is the first one which I mentioned. This has the DE10 Nano along with the RFS module. And this can help you to collect, analyze, and react to the data from the IoT equipment. Okay, you can get the resources from here. And this classic DE10 Nano kit adds Wi-Fi and Bluetooth wireless communication, as well as it also has a wide range of sensors such as ambient, light, temperature, and humidity sensors. Okay. And there was another one on robotics. Okay, that also has been explained, but you can just have a look at it. Go to robotic kits here. So this will take you to a page where we have a self-balancing robot using the DE10 Nano. So this self-balancing robot can implement attitude algorithm, perform motion control, and execute the movements autonomously, moving forward, then turning left and right, object following, as well as obstacle avoidance. All these informations are available. The specifications are provided here, and you can get it. And it also shows that if the lithium battery starts charging and it is completely unable to supply the robot, it is expected up to 2 hours for fully charging. That's what is explained here also. And there is one more on the Terasic Spider. This is also based on the D0 Nano SoC board. But you can refer to those two which I explained. Self-balancing robot as well as the FPGA cloud connectivity kit. Okay. You can select here SoC platform, or you can select bundle solutions, then robotic kits. So in these places, you will have multiple information. So I will stop sharing. If there are any further questions, let me know. And to get details of the Terasic DE10 Nano, again, I am explaining you. Go to Intel Developer Zone and then click DE10 Nano. So when we reach this place, it will take you to the Terasic DE10 Nano kit where you have all the details, which I mentioned in the Terasic website. You can also see that in our Intel website. So you can see the industrial use cases, as I mentioned earlier, IoT systems, industrial automation, and high performance computing. the details of the board, as well as these are the compatible accessory boards. As I mentioned, FPGA cloud connectivity kit is mentioned here. You also have digital camera kit, wireless connectivity board, servo motor kit, multi-touch LCD module, and if you go down, you have multiple projects which I mentioned. Okay, here you can see self-balancing robot and the capture and plot accelerometer data, and this is what I showed you yesterday. Export smart glow and pipe CNN on Intel FPGA. So you will have multiple projects that are available here. And if you click this place, which will take you to build, deploy, and manage your FPGA-based IoT edge applications using the Microsoft Azure. There are 4 modules here. You can try every one of them. For example, you need to first see in the first module, install the Azure IoT Edge runtime. And then in the second module, you are going to build an Azure container. Third module, you are going to build an IoT Edge module that gathers the sensor data and store it in the Azure Container Registry. And the fourth module, we have to reconfigure an FPGA from the Azure cloud using a container application. So if you wanted to get into the details of each and every module, you can click here. This will take you to module by module. So in every module 1, what are the steps that need to be taken? So you require the D8 Nano, and you can create a Microsoft Azure account, and you can start continuing. The steps are provided. So this information is also available in our Jurassic D8 and Nano page. So see in this place, right? Build, deploy, and manage your FPGA-based IoT edge applications using Microsoft Azure. So I will share this link in the chat. I request you to go through that. This may give you a good idea about the Jurassic D8 and Nano kit, where you can choose this kind of boards for SOC projects and also on the IoT applications. Yeah, the link has been shared. You can see that in the chat. Please go through that in detail. Thank you. And even the course summary session slides is also available in the Day-6 folder. Okay, what I explained about the course summary, where I explained you about what was covered in each and every day, starting from day 1 to day 6, what are the topics that has been covered and what are the key takeaways of the training, which has been captured in the slide. That also is present in the Day-6 folder. You can go through that PDF, course summary.pdf. Okay. Okay, so already I have explained, but then still there was a question on the Intel FPGAs for AI. So you can again refer to the pages like Intel FPGAs for AI, where you can see artificial intelligence. Okay, where you can see the resources, white paper, everything here. You have the resource center here, where you can refer technical documentation, videos, and training courses. Also, machine learning with Intel FPGAs, if you see, that will take you machine learning FPGA applications Intel. Please go through these 2 pages. This has been shared with you during the AI session. So if you have not got the details, you can refer it right now. Okay. So I'll share this with you. You can get into the details. Hi, Sumit. Good evening.
Good evening, everyone. Am I audible?
Yeah, you are audible, Sumit.
Okay, great. Thanks. Daddy, we're waiting for 5 o'clock, right? So there is some time.
Yes, we have 3 minutes time, Sumit. Yes.
I just sent you a message. Just have a look. Thanks.
Good afternoon, Gaurav sir.
Good afternoon. Hello, Sumitji. How are you?
Hello. Good evening, everyone. Yes.
So, Viplab,
Yes, sir.
how many people will be joining the event?
Sir, Sangeeta ma'am from IIT Patna have joined.
Okay.
Gupta sir is having some other commitments, so he will not be joining from IIT Jabalpur.
Okay.
Yes, sir.
Okay. So, how long will it take to start?
Sir, actually, it is time for starting.
Okay.
We have proposed from 5 p.m.
Okay. So we can, if or if you are waiting somebody, then we wait, and otherwise we can start.
Yes, sir.
We can wait for 2-3 minutes, sir. Islar needs to join.
Okay. Oh, okay.
just checking if the audience have joined, then we can get started. I'm okay to wait a bit longer if we are waiting for people to join.
Yes, Sumit. Yeah. So I have think Diswar also will also be joining. Good evening, sir.
Evening all. Hey, good evening, Patty. Sorry, I was having some trouble in joining late. Gaurav sir, hi. Sahu sir.
Hello, Starji.
Yeah.
So shall we start?
With your permission, we would like to start a validity session, sir.
Okay.
Just wanted to check. I think Sumit is also there, Patty, correct?
Yes, he is there.
Yes.
Okay. Thanks. Yeah, please.
Very good afternoon to all. I, Biplab Sharma from ICT Academy, IIT Guwahati, welcome you all to the validity session of this 1 week joint faculty development program on designing with FPGAs. Today we are fortunate to have with us Dr. Gaurav Trivedi sir, Principal Investigator of ICT Academy, IIT Guwahati. Dr. Sanjeev Manas sir, Chief Investigator from IIT Roorkee. Dr. Sangeeta Singh, Joint Program Coordinator from NIT Patna. Mr. Sumit Verma, Director Strategy from Intel. Our resource person from Intel, Mr. Isra Sheikh sir. Mr. Padmanabham Kalyanam sir. And all our dear participants. I would like to request Gaurav Trivedi sir to address the participants. Gaurav sir.
Yeah, thank you. A very good evening to all of you. I think we are having Professor Sanjeev Manas from IIT Roorkee, Professor Sangeeta Singh from NIT Patna, Dr. Meena Pachore, Mr. Isra Sheikh, Mr. Sahu, Mr. Padmavan, and my friend Mr. Sumit Verma is also here. So, and all the participants. This particular course, designing with the FPGA with Intel, we have started due to one particular, you can say, collaboration with Intel, and we have to reach approximately 200 faculty members in India, and with that drive and with that motivation, we have started. And it is good to inform, it is good to see that approximately 300 people also this time joined this particular course pan India. I believe that this particular, I'm very much sure that this particular course would have added a lot of value to your learnings and your knowledge base and the nitty-gritties of the Intel FPGAs and how to port your designs, how to validate the design using Intel FPGA, how to use it, that also would have become very much clear to you. Intel is also coming up with its own, you can say, new innovations in FPGA technology, like the FPGAs which support the AI and machine learning. This is something which is quite unique and new, and I believe that the people, in fact, we are also using one at our end, and so we hope that others can also explore this kind of new paradigms in the in the FPGA technology, and you can say boost their research. I wish everybody a very good luck for your future endeavors, and I thank all the ICT academies, IIT Roorkee, NIT Patna, IIT Jabalpur, MNIT Jaipur, to participate wholeheartedly in this particular course. And I believe that even in future we will be having many more such collaborations to develop and to pass the information to the scientific community in the nation. Thank you.
Thank you, Gaurav sir. Now I would like to request Dr. Sanjeev Manas sir from IIT Roorkee to address the participants.
Thank you. And let me first of all start by welcoming and greeting all the participants and the panelists that are present here, and also very warm welcome and also hello to Professor Gaurav Trivedi, who has taken this initiative in floating this program in collaboration with Intel and also other PIs of the co-host academies, and it is really indeed very good experience for all of us to collaboratively work on this particular course. We had about more than 20 participants in this program, and we have overall very good feedback also. FPGA, as Professor Gaurav rightly pointed out, is going to FPGA technology as it is, in addition to its classical or the traditional applications, is expanding into new vistas and new areas, which actually drives applications from machine learning, AI, and enabling technologies. So our effort here is to create a program which gives the introduction to FPGAs, but also the new emerging applications of FPGAs, with the hope that the participants who are faculty members of the engineering colleges are able to then build on from the foundational material and the advances that they learned from this program to take them into the classrooms to build or to create curriculum which is reflecting latest trends and technologies in this area. So it is our sincere hope that by this particular program and other programs that we do in this EICT initiative, the so-called train to trainer and train the trainer and the multiplying effect of whatever materials and the courses that we do in this platform will have significant improvement in the quality and the level of courses and the education and the exposure to the latest technologies that is provided to the students across the country. As you might have known that this EICT Academy is an initiative, it's a unique program which was supported by mighty Government of India. And through this program, we have been able to create a very sort of well-planned programs involving almost all the participants from all the corners of country. Sometimes there are participants from abroad also. So this unique countrywide classroom has created its own impact, and people really appreciate this program, which helped us to minimize the cost in running the programs, bring in the right experts onto the panels and into the programs, and create material which is relevant, run the program which are relevant and in demand, and also required in terms of skill upgradations in various technical institutes around India. So I again thank all the organizers, and I also thank my team here at EICT Academy in supporting this program. And I want to wish and say my congratulations to all the participants who have successfully completed this program. And I wish all the participants all the very best for their endeavors. Thank you very much.
Thank you, Sanjeev sir. Now I would like to invite Dr. Sangeeta Singh ma'am, the Joint Program Coordinator from IIT Patna, to address the participants.
I thank all the participants first of all, because they were the main stakeholders, because we are able to come to.
Dr. Sangeeta, we are unable to hear you properly.
Am I audible?
Yeah, better.
Okay, sir. First of all, I would like to thank our participants because they were the main stakeholders because of whom we thought of organizing such kind of program related to FPGA. And second, I would like to thank Dr. Gaurav sir and Dr. Bharat Gupta sir for in association with that Intel, because this is one of the program that is more inclined towards the industry. As Sanjeev Mahanis sir also indicated that now we are heading towards the another non-conventional uses of these FPGAs like AI, NLP and all. So probably this course can prove as one of the milestones in this domain. All the participants, for them, I just hoped that this 1 week FDP would be something where they can at least start up in the domain if they want to start their research in the particular domain. I'd like to thank all the participants, all the organizers, the entire ICT Academy team, and Dr. Meena from NIT Patna. She is also of the joint coordinator with me, and Bharat Gupta sir, who is the principal investigator of ICT Academy and NIT Patna. Thank you, everyone.
Thank you, Sangeeta ma'am. We have our guest of this program, Mr. Sumit Verma, Director Strategy, Intel India. Sumit Verma is currently the Director Strategy at Intel India. He leads key external alliances in space of innovation, research, business enablement, and strengthens strategic engagements in priority technology areas for Intel in India. He collaborates with governments, both federal and state, industry associations, academia, incubators, accelerators, and bright young innovators in the country, and leads key initiatives like leadership and excellence in academic development programs, design in India, make or innovation in startup ecosystem, grand research for Intel India. Sumit has been with Intel for over 18 years and holds varied skills and knowledge from his technical, business, and management expertise. Mr. Sumit is alumnus of IIT Bangalore and Harvard Business School. Sumit sir, welcome to this program. I would request you to please address the participants and give a small talk.
Well, thank you for the introduction. And I must say that, in this virtual world, it's very difficult to have people even do workshops for, or even participate in meetings for more than 3-4 hours. So having participants, engrossed in the workshop for the entire week, it demonstrates the commendable work that the organizers have done and the content that made the audience kind of stick around for a week. So firstly, I wanted to kind of give a big applause to the organizers and the participants. And I truly hope that this 1 week that you have spent in this workshop was good use of your time. With that, I would also like to, of course, thank ICT Academy for organizing, hosting the entire team, including Professor Gaurav and his team, the Institute. I won't repeat the name of all the faculty members, but everyone involved, a big thank you for the tremendous work done in making this workshop successful. I also want to thank the Intel team, Paddy specifically, and Israr for ensuring proper delivery of content is done. It's not easy to execute these workshops, and Paddy has been able to do it every time so successfully. So thank you, Intel team as well. Well, I know there are 2-3 other people who would like to talk, so I will like to make my discussion very brief. I also want to give a context to the audience, right? Why Intel is doing this, right? So Intel University program that engages with university is called LEAD, which means Leadership and Excellence in Academic Development. Under this umbrella, it has various functions that focuses on accelerating innovation, engineering excellence, enabling business, pipeline for India tech ecosystem, leadership development. Ultimately, it caters for robust and enduring relationship with the academic ecosystem, right? That's the LEAD program. It focuses on high impact research. There are 5 focus areas that the program does. One is high impact research. Second is knowledge exchange. Third is collaborative classrooms. Fourth is talent for the India tech ecosystem. And fifth is executive connect. I won't go into a lot of details, but I wanted to just connect the dots that the workshop that we are doing or was done in this week aligns well for knowledge and innovation exchange that Intel aims to do collaboratively with academia and in a bi-directional manner, saying that if there is something we want to share with the academic ecosystem, at the same time, we hope to learn back from the academic ecosystem. And in this process, both these parties, the academia and the industry, improves and evolves, right? With that, again, thank you for the audience for listening in. I look forward to the feedback of this workshop, and big thanks for the organizers for pulling off this 1 week of FTP so well. Thank you.
Thank you, Sumit sir. Now I would like to request Dr. Meena Pachore ma'am, Joint Program Coordinator from IIT Patna, to address the participants.
Thank you, sir. Good evening to all. It's my great privilege to address you all on behalf of IIT Patna and my team. I would like to thank all the participants for their participation, and we are truly delighted with your presence. I'm very thankful to all speakers for from the Intel for sharing their knowledge with us. I'm also very much thankful to all joint coordinator from the different IIT Academy and committee member from IIT Guwahati and the different institute proctor coordinator who made this FDP functional. And especially I just want to very thankful to Gara sir who has given this chance to participate or work with him. And especially thank you for Rosa madam for her constant help and support at various stages. And this is a very good and useful FDP for the participant. Looking forward to many more such FDP, engaging more people and on a great level. Thank you very much all. Thank you. Thank you.
Thank you, Madam. Now it is time to hear from our experts. I would like to request Isra Sheikh sir to address the participants and motivate them.
Good evening all, and I first of all dignitaries on the dais, professors, thanks for arranging this and the committee for executing it. And Sumit has articulated and he has mentioned that, like, you know, it takes a lot of efforts from our side also to prepare it and deliver it. Good amount of, like, you know, resources has come forward, and they are passionate also about technological deliveries to the people, those who are interested to take it forward. And we see this community is always raising the hand to get them enabled with the technology. So as we are concluding this session now, earlier days, what you have learned it, like, you know, what is the next? What do you want to do the next? How do you want to take up this? So few of the points which I want to the participants to remember it and take it forward is that every learning what you have taken, even a single learning what you have taken from each session, try to implement it. Try to take up to your lab into the discussion. Even if you are taking into the discussion, really that particular idea will innovate you to do something differently which you are doing conventionally. Try to make, people used to say that, like, you know, how you can share the knowledge by way n is to n. N can be any number, you know, and you here by means of this virtual session, it has been demonstrated, like, you know, many people can participate. I was very glad and good to hear that, like, you know, over 300 heads per day participated in this particular program. Now, this is a responsibility of the participants to take to the next level so that you are including it in your sessions, you are exercising in your classroom sessions, you are implementing the ideas and building the new ideas and taking into the lab, whichever colleges we have lab setup, hardware donations are there, don't make them beauty of a shelf. We would be more than happy to see that, hey, Intel team, we were trying to do some experiment. I don't know what, something went wrong, but at one point, the board has broken, it's not working. Good to hear that, it has burned. Do that experiment. These boards are there, these hardware labs are there, these tools are there, you people to do the experiment. Accident may happen in that, but we are there to support you. We are there to help you. There are a lot of resources are there online, a lot of trainings are there available online. A lot of forums are there. Don't rely on one person that I have emailed to that person and but he has not responded me, what to do next. A lot of forums are there, discussions are happening. Intel has dedicated resources to answer your queries on the forum, which I think link has been shared with you people. I would like request you people to all utilize these resources. Make use of these 7 days, what you have invested for bring new innovation in your learning, imparting learning and bringing innovation. And that's a way, you can be a more innovator, research can happen. Intel is looking, Sumit has explained the lead, what are the 6 points are there of that particular program. One is that research, we are looking from academia like you, institutes like those who are participating and organizing, institutes like you people, to come forward and bring new innovative ideas which can be researched together. We are open for that, so I'd like to again thanks to the organizers, congratulations for executing this successfully, and to all the participants, literally, this is one of the sessions which we have seen so many participants coming in, and then you take the advantage of this. Again, this is the program for you. You are the one of the focus centric people in this particular program. Now it's responsibility of you people to take it forward, what is required from Intel to make you people successful any stage. We are there to help you, and a lot of means and resources are there. With this, I would like to thanks again to everyone, and I want to conclude my talk.
Thank you, Isra sir. Now I would like to request our resource person, Mr. Padmanabham Kalyanaraman sir, to address the participants.
Thanks, Biplav. Good evening, everyone. So I would like to thank the participants, all the participants who attended this FDP, for patiently listening the lectures in the morning and then performing hands-on lab in the afternoon. It is not easy. Starting from morning 10 a.m. to 5 a.m., 5 p.m., performing the labs and then also listening to the lectures next day. Right? It is very tedious. I would like to congratulate and thank everyone for successfully completing this course. I would like to thank the organizers, ICT Academy, IIT Guwahati, Professor Dr. Gaurav Trivedi, and all the ICT organizers. And I will also need to thank Israr and Sumit for constantly motivating me and providing support. I would like to thank everyone, and we wanted this kind of collaboration right in future also. Thank you very much.
Thank you, Padmanabham sir. Now I would like to request the participants to share their experience about this program. The participants. Yes, sir.
Biplav, I would
Yes,
like to add only a couple of additions here.
Yes, sir.
We actually want to, you can say, connect with 2,000 faculty members pan India. Okay.
Yes,
and as of now, we have got connected with approximately 1,000 in
Yes,
just
sir.
2 programs. So this is a big success with Intel, I just say it. And I think many more programs in future will enable us to do many more great things. So thank you, team Intel, and thank you, Intel, for being with us. And what Sanjeev Manas has said that also Sanjeev Manas has said specifically that we have to work together for a greater benefit and reach. I hope that will always be there. Thank you.
Thank you, Gaurav sir.
And thank you, Sumitji, Israrji in person, to really, you can say, motivate us to keep going forward. I hope that your support will always be there. Thank you. Please go ahead.
Yes, sir. Dear participants, you can unmute yourself and raise your responses. We request all the participants to share their feedbacks about this program.
Yes, participants can actually, okay, there is one only thanks notice there from Ms. Samai V that thank you so much for this session. It was very informative. Thank you, sir. There are many more in future. Anybody else? I request participants to please come forward and you can say a few words. Okay, so I think there are not many. There are people are not there. So Viplav, you can go forward, please.
Thank you, sir. I would like to request Gaurav Trivedi, sir, to share his vote of thanks, sir.
Yeah, so I have to say I just I include in between it already.
Yes, sir.
So, but yes, I must have to say once again. So first of all, I really thank Intel Technologies. So from all the E and ICT academies for collaborating with us to host such a nice and beautiful course. And we all of us hope that in future we will be hosting many more advanced courses. Okay, not only related with the FPGAs, but sometime I'm to say, but other than FPGAs also would really, you can say, add flavor to this. So that is there, and I really thank all the IIT academies in person, and on behalf of IIT Academy, IIT Guwahati, that due to you, we have a really very successful course. So with this, I really thank once again, thanks all the participants as well in their I'm to say uh, they have found some time out and they attended this course. But yes, I just second Mr. Israr Sheikh that whatever you have learned, you have to take it forward, and that is your responsibility. And if you want to connect with Intel also, you can always use our channel. We will be able to connect with Intel for many other you can say suggestions, solutions, or maybe some kind of consultancy for the FPGAs or so. So you please do not hesitate to contact us for that. And but again, a big thanks to you. Without you, this program wouldn't have been successful. And I wish everybody a very happy and healthy stay in future. And a couple of messages which are actually posted in the chat section, I will read. Mr. Dibentu, he is saying to the thank you, sir, for the workshop. I am outside, so couldn't open the mic. The course was very beautiful, and I want to be the part of the future course on FPGA like this as well. Thank you, sir. From Tamil Silvi, that was a great experience and very informative. Thank you for all the wonderful sessions. And Dr. Shaheen Khan also saying that very informative sessions. So I want to say this is all. I just said a big applaud to the team Intel and Intel India Technologies. Thank you. And thanks Viplav for hosting, for helping us to arrange this, coordinate the courses. Thank you.
Thank you, Gaurav, sir. With this, we are coming towards the end of this joint faculty development program on designing with FPGAs. In case of any queries, the Telegram group is always active. Dear participants, you can raise your queries in the Telegram group as well. The certificates of participation to all the eligible participants will be shared within next few weeks in a phase-wise manner. So it will be sent to all in a phase-wise manner, one by one. So in case you have some of you may have not received the certificates on the same day, it may be sent on date later after the date in a sequence manner. Hope all of you have filled the feedback form. It will help us to improve. If you have not filled, kindly fill the form. It has been shared with you all in the Google Drive link in the announcement page. It was a wonderful meeting you all, and hopefully we will be meeting again in our future programs. In case you want to organize such courses in association with ICT Academy IIT Guwahati, you can write us in our email ID. and you can also log on to our website for future details. Till then, stay safe and stay healthy. Thank you all.
Thank you all.
Thank you, everybody. Viplav, I'm signing off now. Thank you.
Thank you.
Hello, Viplav. Sorry. Hello, Viplav.
Dear participants, you can now disconnect. We will be closing in another 1 minute.